Hello there, and welcome to Life Beyond Seen, where we take big, complicated pieces of science and turn them into something you can drift through at your own pace. Tonight we're settling into a subject that sits far below sunlight, ships, storms, and every familiar thing on the surface. It waits in a stretch of ocean most of us will never stand near, let alone see, the Kermadec Trench. A place so deep that if you dropped Mount Everest into it, the peak would sit more than a mile below sea level. A place so remote that most maps don't bother giving it more than a thin blue line. A place we talk about like it's reachable, even though it behaves more like a locked room at the bottom of the world. Before we wander downward together, I'd love to know where you're listening from tonight. Somewhere near a coastline, somewhere inland. Maybe you're lying in bed with a soft lamp nearby, or settling into a quiet moment after a long day. And what time is it for you right now, in your part of the world? The idea of you sitting comfortably while we talk about a place that would crush a submarine flat in seconds is oddly grounding. Two extremes sharing the same moment. If you find this slow dive soothing, or if you like learning about the strange corners of the planet that don't usually get much attention, I'd be grateful if you tapped the like button or subscribed. It helps this space stay calm, helpful, and easy to find again when you want something steady to relax with. The Kermadec Trench isn't just another deep spot on a map. It's one of the deepest cuts in Earth's crust, stretching from the northeast of New Zealand up toward Tonga, created by the grinding collision of tectonic plates. When you hear collision, you might picture a sudden crash. This one is nothing like that. It moves by inches each year, yet those inches carve a canyon wider, darker, and more extreme than any mountain range you've ever seen. It's a world where darkness is not a dramatic idea, but a simple, absolute fact. No flicker, no dim glow. Just a straightforward absence of light because the water above it stacks so high that not even stray photons can slip through. It might be tempting to think that with all our technology, all our submersibles, satellites, sensors and clever machines, we could go down there. It sounds like something we should have figured out by now. We've stood on the moon, sent robots to Mars, watched comets up close, and measured black holes using light that started travelling before cities even existed. So a trench in the ocean should be manageable, at least in theory. But the reality is different. The Kermadec Trench remains one of the least explored places on Earth, not because we don't want to study it, but because almost nothing we build can survive long enough to do the job. Not yet, and maybe not for a long time. Imagine stacking the weight of a small city on top of a single fingernail. That's roughly the pressure at the bottom of this trench. Scientists can calculate it with neat numbers, but the experience of trying to design something that won't collapse under that force is less neat. Most materials behave perfectly well at normal depths. Lower them a bit farther and they start creaking. Go deeper and they deform. Keep going and they snap. The Kermadec Trench pushes beyond anything that feels reasonable. Everything down there is designed by the environment itself, shaped over millions of years to survive pressure that would instantly crush metal and shatter glass. It's also unbelievably cold. Not dramatic fantasy-level cold. Just a simple, consistent chill, near freezing that slows chemical reactions, interferes with electronics, stiffens moving parts, and makes energy use unpredictable. Even if a machine could reach the bottom without turning into an expensive pancake, it would still need to operate in an environment where everything it relies on behaves differently. Batteries drain faster, sensors misfire, lubricants thicken, and electronics start to drift away from their expected behaviour. This isn't a gentle inconvenience, it's a continuous reminder that the deepest parts of the ocean run on rules that don't match the ones we rely on closer to the surface. The darkness adds its own complication. There's no natural light to help instruments orient themselves. Everything must carry its own illumination, and as soon as you turn on a light, you change the environment you're trying to observe. Many of the creatures down there respond to even the slightest glow. They scatter, hide, or simply vanish into the darkness the moment the beam switches on. You can't blame them. Their entire world is shaped around the absence of light. A single spark from a submersible is like setting off a flare in a quiet room where nobody expected company. Communication is another problem. Radio waves don't travel well through seawater, neither do GPS signals. Most of the tools we use to navigate on the surface are completely useless at these depths. Instead, explorers rely on cables that stretch miles down from a surface ship. But cables add their own limitations. They can snap. They sway with currents. They have weight. The deeper you go, the more cable you need, and the harder it becomes to maneuver anything attached to it. A trench that reaches nearly 10,000 metres adds complications that would make even the most enthusiastic engineer sigh. Even if we sent the perfect machine down, the landscape itself is unpredictable. The seafloor near tectonic boundaries is constantly shifting, not in dramatic cinematic jolts, but in small movements and slow adjustments that gradually reshape the terrain. Slopes shift, sediment drifts, entire sections can slide under their own weight. Something might be stable for a few years and then suddenly give way. If a machine is down there when that happens, it won't come back. Despite all this, the trench is not empty. Life survives there in forms adapted to pressure, cold, and darkness. Not glowing, fantastical creatures, but real organisms built to deal with conditions most of us would call impossible. Studying them would tell us a lot about life's resilience, about how biology adapts, about how ecosystems function in extreme settings. But the challenge is simple. Getting to them is the hard part, and staying with them long enough to understand them is even harder. This gap between curiosity and capability is what keeps the Kermadec Trench out of reach. We want to know what lives there. We want to know how the geology works. We want to understand the chemistry, the biology, the movement of water, the cycles of nutrients, the shape of the land. But wanting and doing are not the same thing when every step forward requires tools that behave differently than expected, and materials that don't last long enough to collect the data. Still, the attempt continues. Researchers send down landers, they send pressure-resistant cameras, they run seismic studies, they model the trench using computer simulations based on whatever limited measurements they can gather. Every bit of data helps, even if each piece comes from a machine that may not survive the journey. Progress is slow, steady, and rarely dramatic, but progress all the same. So tonight, as we start sinking into the details of why we can't truly explore the Kermadec Trench, we're not telling a story about failure. We're telling a story about limits. Limits set by physics, by biology, by engineering, and by the simple reality that not every corner of our planet opens itself up easily. Some places insist on being distant. Some places resist our curiosity not because they hide anything mysterious, but because their environment is bluntly unforgiving. As we continue drifting deeper into this subject, you'll see how those limits overlap, reinforce each other, and shape our ability to explore. You'll also see why this trench remains, for now, a place we can describe from afar but barely touch in person, or even with machines. And while that might seem like a barrier, it's also a reminder that our planet still holds places that test the edge of what we can do. Places that aren't impressed by our confidence or our technology. Places that simply exist on their own terms. And with that steady picture in mind, let's move a little further down into what makes this trench so difficult to reach, and why even our best machines struggle long before they get close to the bottom. The Kermadec Trench sits in a part of the Pacific where the surface gives almost no hint of what lies beneath. If you looked at it from a ship, you'd see nothing unusual. A steady horizon, maybe a breeze, maybe a shifting line of clouds. If you dropped a camera over the side, the water would look the same as any other deep part of the ocean. There's no sign announcing that the ground suddenly falls away into one of the deepest cuts on Earth. No cliffs, no dramatic chasm. Just a vertical distance so long that it turns from water into weight. This is what makes the trench so strange. You don't meet it the way you meet mountains or valleys on land. It reveals itself only after a long, steady descent through layers of ocean that seem silent, simple and endless. The Kermadec Trench stretches for more than 1,000 kilometres, running northeast from New Zealand up toward Tonga. It's part of a vast system of trenches formed by the slow collision of tectonic plates. On one side you have the Pacific Plate, huge, old and restless. On the other side is the Kermadec Plate, smaller but still powerful in its movement. When the Pacific Plate pushes beneath the other, it pulls the seafloor down with it, carving a long arc that deepens and sharpens over millions of years. This process, called subduction, is slow enough that you'll never feel it happening, yet strong enough to bend the crust of the planet downward until it becomes one of the deepest places on Earth. In a way, the trench isn't just a physical place, it's the visible mark of the Earth's interior at work, reshaping its surface bit by bit. The first thing people notice when they study the trench isn't the depth, it's how remote it is. The nearest coastlines are far away. Shipping lanes rarely pass over it. Most research vessels don't travel near it unless they have a very specific reason. Even the weather can be challenging. Storms develop quickly in this region, driven by the open Pacific. Large swells rise without warning. A calm day can turn rough within hours, and because the trench sits so far from land, support and shelter aren't easily available. Exploring it means committing to long journeys, uncertain forecasts, and expensive equipment that must survive unpredictable conditions before it even touches the water. As you move downward from the surface, something subtle changes long before the trench comes into reach. Light fades, not suddenly, but gradually enough that you don't notice the transition until you look back and realise the glow from above has shrunk. It turns from white to blue, then from blue to a deeper shade that feels heavier in the water. Sunlight becomes less useful with every metre. Eventually it vanishes completely, leaving only darkness and whatever artificial lighting we bring with us. This isn't just an atmospheric moment. That loss of light marks the first major separation between the world we know and the world the trench belongs to. The water becomes heavier as the descent continues. Pressure increases with every 10 metres, stacking weight on weight until the familiar rules of buoyancy and structure begin to shift. Most submersibles built for research can handle moderate depths. Some specialised ones can manage several thousand metres. But the Kermadec Trench pushes beyond the comfort zone of nearly all of them. It forces every joint, tube, cable and hull to behave differently. Materials that feel sturdy in your hands on deck start bending deeper down. Electronics that function smoothly in a lab become sluggish or unresponsive. Lights dim or fail more easily. Even sound travels differently, changing the way Sonar maps the landscape. That landscape is not smooth. Trenches form sharp angles and steep walls that drop down like underwater cliffs. In some places the slope is gradual, layered with sediments washed down from above. In others it becomes abrupt, jagged and unpredictable. Landslides happen here, though not in the dramatic rush you'd imagine from the surface. Some shifts occur over hours or days as loose sediment drifts downward. Others happen more quickly when the seafloor adjusts to tectonic pressures. These movements reshape the terrain without notice, making it difficult to predict where anything will settle or how stable a particular area will remain. What makes the trench even more challenging to picture is that the bottom isn't just a narrow crack, it's a long, uneven valley. In some places the floor widens out, almost like a plane. In others it tightens into a steep, narrow corridor with pressure pushing from all sides. The depth varies along its length, reaching more than 10,000 metres at its deepest point. That depth is difficult to grasp without comparing it to something familiar. If you stacked the world's tallest skyscrapers on top of each other, they would disappear far above you and still not reach the surface. If you dropped Everest into the trench, it wouldn't even peak above the water. It's not simply deep, it's depth beyond anything we live with. Moving through the trench requires machines that can tolerate crushing pressure, but the deeper you go, the fewer options exist. And unlike other trenches that have been studied more thoroughly, the Kermadec Trench has less recorded data. The lack of previous exploration means every descent is, in a sense, a first descent. There are fewer maps, fewer samples, fewer photographs, and fewer reliable models. Even when scientists analyse sonar readings of the trench, the images are often blurred or incomplete. Mapping a trench this deep means sending sound waves through miles of water, and water absorbs and scatters those signals the farther they travel. That distortion leaves gaps in the data, pockets of uncertainty, and entire sections that must be interpreted rather than directly observed. Despite that uncertainty, the trench is not empty of life. It hosts organisms that have adapted to pressures that would flatten almost anything else. Some are small, slow-moving creatures that drift above the seafloor. Others burrow into sediments or cling to rocky outcrops. Many of them have never been seen clearly, partly because cameras rarely function long enough at that depth to capture extended footage. The creatures here don't glow brightly or move gracefully. They survive with minimalist designs shaped by the extreme environment. Soft bodies, flexible structures, and metabolisms that run on minimal energy. Studying them could tell us a great deal about biology under stress, about how life persists when conditions are at their absolute limit. But reaching them is difficult, and staying with them is even harder. One of the most striking things about the trench is how stable and unstable it is at the same time. The water above it is calm compared to the chaos of surface waves, yet the ground beneath it can shift. Sediment settles, then moves again. Gas pockets form, then drift upward. The tectonic boundary beneath the trench is always active in some way, though not always in ways we can easily measure. It's a place shaped by slow processes measured in centuries and quick processes measured in hours. That combination makes it unlike any environment humans interact with directly. For researchers, the trench isn't just a target of curiosity, it's a missing piece in understanding how Earth's oceans work. The deep trenches act as pathways for water movement, chemical cycling, and geological activity. They store carbon, influence earthquakes, and host ecosystems that function independently of sunlight. The Kermadec Trench, in particular, occupies a region of the Pacific that connects different oceanic systems. Understanding it could help explain how nutrients move, how tectonic forces interact, and how deep-sea life evolves. But exploration has been slow because each question leads to another challenge in simply reaching the area where the answers lie. When scientists talk about the trench, they often describe its scale with numbers, but the numbers never quite convey what it means to descend through mile after mile of cold, heavy water into a space where everything you know behaves differently. The trench is not a dramatic canyon with sharp edges and open views. It's a silent, compressed world where distance feels different and direction depends entirely on instruments. You don't look around. You observe through screens. The environment doesn't welcome visitors. It doesn't fight them either. It simply remains indifferent, shaped by physics far older than anything we've built to explore it. For anyone trying to understand the trench, the first meeting is not with the deepest point. It's with the realization that reaching it is as difficult as studying it. The depth creates barriers, the pressure creates limits, the remoteness creates logistical challenges, and the environment creates uncertainty. All of these together form a place that remains mostly untouched. Not because we lack interest, but because the trench demands more from our technology than we can currently provide. As we continue sinking further into why this specific trench feels so unreachable, it becomes clearer that the difficulty isn't in locating it on a map. It's in what happens once we try to enter its world and understand what lies along its unseen floor, where the weight of the ocean presses harder than almost anywhere else on Earth. Reaching the depths of the Kermadec Trench means stepping into an environment where pressure dictates every outcome, every movement, every sound, and every possibility of survival. Most people imagine deep sea pressure in quick comparisons, like a truck on your chest, or like carrying a mountain. These are attempts to make the numbers feel familiar, but no familiar image truly captures what happens when you move through 10,000 metres of water stacked above you. Each 10 metres adds another atmosphere of pressure. At the deepest points of the trench, that adds up to more than 1,000 atmospheres. It means every square inch of anything in that environment has to withstand a force far beyond what most materials ever experience. Pressure at this scale doesn't simply squeeze, it reshapes. It changes how matter behaves. It sets limits that technology has to meet before it can even begin to function. Much of what we know about the trench is shaped by pressure before anything else. Pressure controls the design of vessels. Pressure dictates how thick the walls must be. Pressure determines which instruments fail first, and which may last a little longer. The crushing force isn't sudden or violent. It's steady, absolute, and constant. Unlike storms, earthquakes, or other dramatic natural forces, deep-sea pressure doesn't surge. It doesn't strike. It just exists at full strength all the time, without breaks, without moments of relief, without anything resembling mercy. This is why the deeper you go, the fewer machines can follow. Every piece of equipment has a breaking point, and the depths of the Kermadec Trench sit far beyond the breaking point of most known materials. On the surface, water feels lightweight. You swim through it. You lift your arms without resistance. You move freely. At depth, the weight of water becomes something else entirely. It exerts force equally in all directions. A submersible hull doesn't just hold back water. It has to resist the force pushing inward from every angle. There's no safe direction to shift that load. There's no part of a vessel that escapes the strain. And unlike air, water does not compress easily. Once pressure rises, there's no cushion. The deeper you go, the more the environment closes in. It's not an emotional description, it's a mechanical fact. Engineers designing deep-sea systems measure that load in precise terms. Each square centimetre holds the weight of several cars stacked on top of it. Multiply that across an entire submersible hull, and you get numbers so large that even small weaknesses become catastrophic points of failure. One of the biggest issues with deep-sea pressure is material fatigue. Metals used on the surface behave predictably. They flex a bit. They return to shape. They withstand force without much trouble. At extreme depths, metals no longer behave like the materials we're used to. They compress, and in that compression their molecular structure shifts. Small imperfections turn into cracks. Minor stresses become major faults. A weld that seemed perfect during construction becomes a failure point. A bolt that held steady at 2,000 metres bends at 6,000 and shatters at 9. Engineers constantly adjust designs to compensate for these changes, but the reality is that even the best metals reach their limits, long before the Kermadec Trench begins to level out. Titanium is one of the strongest materials we can realistically use to build deep-sea vessels. It's resistant to corrosion, strong under stress, and has been used for submersibles exploring other trenches, including the Mariana. But titanium is expensive, difficult to machine, and unpredictable at extreme pressures when combined with complex shapes or joints. Even a thick titanium sphere must be engineered with precision that leaves almost no room for error. A perfect sphere distributes pressure evenly. A slightly imperfect sphere does not. That small deviation becomes a place where stress concentrates, and deep-sea pressure exploits that weakness instantly. This is why many deep-sea vehicles avoid traditional windows. Glass, even thick pressure-resistant glass, has limits. The deeper you go, the closer it gets to those limits, and the consequences of failure are immediate and total. Instead of windows, cameras are used. But even cameras require protective housings, pressure-balanced systems and materials that won't collapse. Electronics inside must endure both pressure and cold. And the pressure doesn't just act on housings, it affects chemical reactions, electrical components, and even the flow of energy in circuits. What often surprises people is that the pressure doesn't feel dangerous once you're within a vehicle built to withstand it. The danger exists outside the hull. Inside, everything feels normal. But that normality depends on the hull remaining intact. The smallest fracture undermines everything. A breach at extreme pressure doesn't resemble a leak or a crack. It happens instantly. Water floods in faster than a person can react, compressing air violently and destroying everything inside. There is no partial failure. There is no slow warning. This is one of the main reasons humans rarely descend into the Kermadec Trench. The margin for error is too thin. The environmental load is too high. The equipment needed is too specialised and too fragile to risk without absolute necessity. The pressure also affects remote instruments. Landers, free-falling platforms equipped with sensors, are often used in deep-sea research. They don't require humans on board, so they can tolerate failure more safely. But even these devices struggle. Pressure crushes structural frames, batteries malfunction, buoyancy materials compress, communication modules crack, engineers create syntactic foam to provide buoyancy at extreme depth. It's filled with tiny hollow spheres that resist compression, but even syntactic foam has limits. At the deepest layers of the Kermadec Trench, it begins to compress enough that buoyancy calculations become unreliable. If a lander compresses too much, it becomes too heavy to rise again. Some instruments are oil-filled to resist pressure, as oil does not compress the way air does. But oil-filled systems have drawbacks. Leaks are difficult to detect. Temperatures alter oil viscosity. Pressure still acts on every outer surface, so even these designs require strong housings. Some electronics are pressure neutral, meaning they're built to withstand pressure without special housings at all. But this approach has its own issues. Materials behave differently when directly exposed to pressure. Insulation must be perfect. Connectors must be designed to prevent seawater intrusion, and these systems often fail long before they reach full trench depth. The crushing force also influences how sound travels. Sonar is essential for mapping the seafloor, but high pressure and density affect sound speed. The deeper you go, the clearer some sound paths become, while others warp or reflect unpredictably. This makes mapping the trench floor difficult. Sound waves behave differently depending on both depth and temperature, and in trenches, temperature and pressure change in distinct layers. The result is that sonar images often come back with distortions or missing information. Researchers interpret these gaps as best they can, but the lack of clarity leaves many questions unanswered. Pressure also shapes the creatures living there. Their bodies do not collapse because they're designed for an environment where pressure is normal. Their cell membranes are built to function under intense force. Their proteins operate differently. Their enzymes adapt to slow chemical reactions caused by pressure. These organisms don't resist the environment. They match it. The deeper you go, the more biology loses resemblance to what we know. Instead of bone-reinforced bodies, you get soft structures. Instead of fast metabolisms, you get slow processes tuned to extreme conditions. Humans cannot adapt this way. Our organs depend on specific internal pressures. Our lungs collapse long before we reach even a fraction of the trench's depth. Even specialised diving suits can't approach the required limits, which is why any attempt to reach these depths must be mechanical, not biological. Pressure at this scale also complicates movement. Submersibles must be streamlined, but they also need thick hulls. Thicker hulls increase weight. More weight requires more buoyancy. More buoyancy requires more syntactic foam. More foam increases size. Larger size requires more power. More power requires more batteries. More batteries require more housings. Every decision creates a chain reaction, and each adjustment increases the load on the overall structure. When designing for extreme pressure, engineers constantly balance trade-offs. Reduce weight too much and the hull becomes weak. Increase strength too much and the craft becomes too heavy to rise. The trench does not offer a forgiving envelope for these calculations. It pushes every design to the edge. The silence of the trench comes not from the absence of sound, but from the inability of most instruments to function well enough to record it. At shallow depths, marine environments are full of sound from currents interacting with landforms, creatures communicating, and even distant storms. Deep trenches lack much of that. The water is still, the creatures slow-moving, the geological shifts subtle. Machines that descend there often fail to capture these faint sounds, because the pressure alters the sensitivity of microphones or destroys them entirely. Even communication between a deep-sea craft and a ship above becomes limited. Acoustic signals must travel upward through dense, cold water. Pressure changes the path of these signals, bending them or scattering them. A simple message may take several seconds to reach the surface, and it may arrive distorted. This delay and distortion complicate control. Operators cannot simply steer a craft in real time as they would on the surface. They plan motions in advance, and they accept that the craft may become temporarily unreachable if signals bounce in unexpected ways. Because of all this, the trench remains a place we can barely visit. And even when we do send machines capable of reaching the depth, they rarely remain functional long enough to gather extensive data. Pressure is relentless. It breaks systems designed specifically to resist it. It reduces exploration to brief encounters, short samplings, and limited observations. Every mission is a battle not against unpredictability, but against certainty. The certainty that pressure will eventually win. This doesn't mean exploration is impossible. It means exploration requires tools and materials beyond what we use for most scientific work. It means each attempt pushes engineering forward. It means progress is slow, because progress demands equipment that can endure a test unmatched on the planet's surface. As we look more closely at what this pressure does to machines, and how engineers attempt to counter it, we begin to understand the trench not as a simple geographical feature, but as an environment with its own rules. These rules determine whether a mission succeeds, whether samples return, and whether sensors survive long enough to record meaningful information. Every exploration effort becomes an effort to work within those rules rather than against them, and as we continue forward, the story of pressure blends with the challenges of darkness, cold, shifting terrain, and technological limits that shape everything we attempt in the deep. Descending toward the Kermadec Trench means moving through a world where light fades long before the landscape reveals itself. At first, the loss of light seems gentle. Sunlight softens into a pale glow filtered by the upper layers of water. Colours shift as you go deeper. Reds fade first, then oranges, then yellows. Greens hold on longer, but eventually even they dissolve into the blue-grey that fills most of the mid-water zone. For a while, it feels like dimmer versions of the surface world are still accessible, as if the sun is simply taking its time leaving the room. But that impression disappears steadily. Light doesn't just fade, it vanishes. It becomes something the ocean no longer recognizes, and by the time a vehicle draws near the depths of the Kermadec Trench, light is not merely absent, it is irrelevant. Sunlight stops reaching the ocean somewhere between 800 and 1,000 meters deep. That depth varies depending on water clarity and the amount of sediment suspended in the water, but the general truth is that the deeper ocean is not dim. It is completely dark. Past that threshold, the ocean becomes a world built around the absence of light, a place where vision is no longer an advantage and where creatures adapt by abandoning the need for it. Because light can't reach them naturally, they've evolved without relying on eyes or colours or anything that depends on the sun's presence. That same limitation also applies to us. Every attempt to descend, to observe or to measure relies on artificial illumination that changes the environment the moment it switches on. Understanding why light cannot follow us down requires a clear picture of what water does to it. Water seems transparent on the surface. We can see through it in pools, lakes, or shallow coastal zones. But the transparency is deceptive. Water absorbs and scatters light far more effectively than air. Even a small amount of depth blocks most wavelengths. The ocean is filled with particles, microscopic life forms, and layers of water with different densities. Each of these factors bends light, breaks it apart, or eliminates it entirely. Water absorbs long wavelengths first, which is why red light disappears quickly, leaving only blue at moderate depths. but even blue light eventually breaks down. By the time you reach a few hundred meters, almost all natural light is gone. The deep ocean is the largest continuous dark zone on the planet, stretching around the entire globe. This darkness shapes the environment more thoroughly than pressure or cold. Pressure affects structure, cold affects energy, darkness affects perception, communication, behavior, and survival. For machines, it affects navigation, sensing, imaging, and data collection. The deeper the trench, the less information light can provide, because light simply doesn't exist there unless we bring it. And the moment we bring it, we interrupt the very environment we want to study. Artificial light doesn't behave the same way underwater as it does in air. It doesn't travel far. It reflects off particles and turns into glare. It creates halos instead of beams. Even powerful floodlights lose intensity after a few meters. The deeper we go, the more pronounced this effect becomes. Submersibles use lights to navigate, but the lights illuminate only a small circle around them, leaving everything else hidden. No matter how advanced the design, illumination under extreme depth is always limited by physics. In a trench like the Kermadec, illumination works like a flashlight in fog, revealing only what sits close enough to reflect light directly back. Everything else remains invisible. This limitation might sound like a technical inconvenience, but it shapes nearly every attempt to explore the trench. Cameras depend on light. Without light, sensors have to rely on sound or on mechanical sampling. Visual mapping, which works beautifully near the surface, becomes nearly useless. Even when a camera captures an image, the colours are misleading because water absorbs wavelengths unevenly. A red object might look black, a yellow object might look grey. Shadows become deeper than expected and objects blend into their surroundings. Scientists must interpret these distorted images with caution, knowing that the picture is incomplete at best. Darkness also means we can't easily detect movement. A fish drifting just outside the range of a submersible's lights might remain invisible. A sudden shift of sediment could occur unnoticed. A creature passing by at a distance might never register. The trench is full of life that operates comfortably in this darkness, but our instruments are not built to find it without altering the scene. The lights we bring startle small animals. They drift away or hide in the sediment. Even slow-moving creatures react to illumination because light is foreign to them. Every time we turn on a lamp, we create a bubble of artificial conditions that doesn't represent the trench as it normally exists. Sonar helps navigate in dark zones, but sonar has its own limitations. The sound waves must travel upward and downward through layers of water with different temperatures and densities. They can bend, scatter, or reflect unpredictably. The deeper the environment, the more complex these interactions become. Sonar maps can give broad outlines, but they often lack fine detail. They miss small outcrops, narrow ridges, or subtle slopes. Darkness hides these features visually, and sonar masks them acoustically. Darkness also influences our perception of space. On land, we judge distance by the way light reflects, the edges of objects, and the contrast between different surfaces. Underwater, at extreme depth, those cues vanish. A seafloor ridge might look flat. A steep drop might look like a gradual slope. A large rock might appear the same size as a small one. Even if a pilot sees something clearly, the lack of reference points makes it impossible to judge scale. The darkness erases both the large and the small, leaving everything reduced to shapes within a limited halo of visibility. Creatures in the trench have evolved solutions to this problem. Some rely on touch or chemical signals. Others use bioluminescence to communicate or attract prey. But bioluminescence is not bright enough for human instruments to use for navigation. A tiny flicker from a shrimp doesn't reveal the terrain. It only confirms that something alive is nearby. The deeper one travels, the rarer these flashes become. Bioluminescence thrives in the mid-water zone but becomes sparse near the deepest points where energy is scarce. Hunger is constant in these depths, and even the organisms adapted to darkness use their light carefully to avoid predators. Human senses, of course, are useless at these depths. We cannot rely on our eyes, ears, or hands. Everything depends on instruments, and those instruments depend on artificial illumination. Without light, cameras can't record. Without recording, researchers can't analyse. Without analysis, the trench remains a blank space. And even with artificial light, the trench reveals only partial glimpses. The darkness also contributes to the difficulty of deploying instruments. Remote vehicles often need to land gently on the seafloor. Doing this without visibility is a delicate process. A vehicle may drift slightly to the side, land on a slope, or settle on unstable sediment. It may end up leaning, buried, or tilted. Any of these outcomes can damage equipment or compromise data. Precise landing requires visibility, but visibility requires illumination, and illumination disturbs the environment. Every solution introduces a new problem. Darkness becomes even more challenging when combined with the temperature and pressure of the trench. Lights generate heat. Electronics generate heat. In shallow water, heat dissipates easily. In deep water, heat dissipates slowly. Lights must be strong enough to illuminate, but not so powerful that they overheat. Powerful lamps crack under extreme pressure if not built correctly. Their housings must be thick, which makes them heavier. Heavier lights require more robust mounting systems. More robust mounts increase overall weight. Increased weight demands more buoyancy. More buoyancy requires syntactic foam, which compresses. Every attempt to brighten the darkness leads to a cascade of engineering adjustments. Some teams attempt to reduce reliance on light by using sonar imaging systems, but sonar cannot replace optical clarity. Sound waves reveal shapes and distances, but not details. They show where objects are, not what they are. A sonar map might identify a rock formation, but it cannot distinguish between a rock and a living organism resting motionlessly on the seafloor. To understand biology, geology, and ecology, researchers need visual information, and visual information requires light. Some engineers have experimented with red light or infrared illumination, hoping it might disturb animals less. Unfortunately, water absorbs infrared almost immediately. Red light disappears faster than any other colour. Even high-powered beams vanish within a short distance. Blue light penetrates best, but even it has severe limits in the deep. A blue lamp might illuminate a few meters ahead, but beyond that zone everything falls into silence and shadow. Darkness also affects how time functions during an exploration mission. Without daylight cycles, without the faint glow of the sun, everything becomes a monotone experience. It's easier for operators to lose track of time while monitoring a vehicle in the deep. Hours blend. The only rhythm comes from data transmissions, status updates, and the slow descent or ascent of the vehicle. Darkness becomes the standard backdrop against which all progress happens. There is also the psychological side. Humans do not naturally respond well to total darkness. Our minds are wired to interpret shapes and detect movement. Darkness removes those cues. Even though no one physically descends in most trench missions, the operators on the surface still experience the tension of monitoring something they cannot see in real time. The vehicle is alone in a black expanse, moving through an environment where visibility is measured in meters rather than kilometers. Every action is deliberate. Every decision carries risk. Without illumination, every step feels uncertain. The darkness is not dramatic. It's not threatening. It's simply complete. It doesn't change. It doesn't flicker. It is the most stable aspect of the trench environment. It is always present, surrounding everything, unchanged by weather, season, or time of day. To explore the trench means accepting that you enter a world where light is not a natural resource. It must be created, managed, and controlled. Even if we someday build better lights and stronger cameras, the darkness will always limit how far those improvements can go. Water will always absorb and scatter photons. It will always restrict optical range. It will always distort colours. No technology can change the physical properties of the ocean. At best, we can work within those properties, pushing the limits but never eliminating them. This is why darkness is one of the central reasons we cannot fully explore the Kermadec Trench. It removes our most reliable source of information. It forces us to rely on tools that alter the environment. It limits navigation, mapping, sampling, and observation. It creates uncertainty that pressure, cold, and remoteness then amplify. Every challenge compounds the others, turning exploration into a slow, methodical process carved out in brief windows of visibility. As the journey continues downward, the darkness remains constant, but the environment grows increasingly complex. The pressure increases, the cold intensifies, the seafloor rises and falls unpredictably, and together these factors create a place where even the best designed machines must struggle to function. Moving forward, the story shifts from the absence of light to the limitations of the tools we send down, and why those limitations keep the trench hidden despite our attempts to uncover its secrets. Designing machines for the Kermadec Trench begins long before anything touches the water. In fact, many of the machines built for this environment fail during planning, construction, or preliminary testing. Failure in this context isn't dramatic. It's not a sudden collapse or a catastrophic implosion, though those do occur during full-depth trials. More often, failure means a simple realization that the intended design will not survive the descent or cannot function under the environmental conditions that define the trench. The machine never becomes a prototype, never leaves the workshop, never reaches a ship deck. It fails before it begins because the physics involved leave no room for compromise. Every step toward the trench is dictated by conditions that do not adjust themselves to our expectations or desires. They demand strict obedience to their rules. Even at the earliest planning stages, engineers must contend with the fact that deep-sea machines are fundamentally different from machines built for surface or even mid-depth operations. Submarines, remote-operated vehicles, sensors, cameras, and sampling devices that work beautifully at a few hundred meters instantly become inadequate once the target depth reaches several thousand meters. It's not a gradual decline in performance, it's a hard divide. The moment the depth requirement crosses a certain threshold, the design process must transform into something closer to aerospace engineering than marine construction. At these depths, pressure behaves the way vacuum does in space. It tries to crush instead of pull, but the unforgiving nature is the same. The first wave of failures often occurs while evaluating materials. In theory, engineers have many options: steel, aluminum, titanium, ceramics, composites, syntactic foam, glass, and specialized plastics. But the deeper the target, the fewer of these remain viable. Steel is strong but prone to corrosion and too heavy for many designs. Aluminum is light but lacks the structural resilience. Ceramics can withstand extreme pressure but fracture unpredictably. Plastics deform too easily. Glass crushes. Even syntactic foam, designed specifically for buoyancy at great depths, compresses. The options narrow until titanium, certain composite structures, and a handful of pressure-balanced technologies remain. But these are expensive, difficult to manufacture, and sensitive to tiny imperfections. At this stage, machines fail on paper. Models show that the hull thickness required would make the vehicle too heavy. Calculations reveal that the necessary buoyancy would exceed practical limits. Stress analysis indicates that joints or connections would buckle. Sensors cannot operate under the expected load. Cameras cannot maintain clarity. Batteries cannot function long enough in the cold. Each of these issues appears before anyone touches a wrench. Engineers must either redesign or discard the entire approach. For machines that do reach the prototype phase, the next hurdle involves pressure testing. Much of this occurs in specially built pressure chambers that simulate deep-sea conditions. Engineers place housings, joints, lights, cables, batteries, and metal frames inside these chambers and subject them to pressures equivalent to thousands of meters of seawater. These tests often reveal weaknesses that were not obvious during simulations. A housing might deform slightly. A weld might reveal micro-fractures. A transparent dome might appear perfect until a small bubble of air trapped inside causes sudden failure. Sometimes the chamber tests reduce a piece of equipment to fragments. Sometimes they simply show a slow leak that would have become catastrophic at greater depths. Many machines fail in these chambers because pressure does not behave in intuitive ways. It concentrates force on corners, edges, seams, and any spot that differs from a perfect curve. A tiny manufacturing defect, invisible without magnification, becomes the point of collapse. Even if a structure survives the pressure chamber, that doesn't guarantee survival in the trench. Pressure chambers usually simulate only static loads. The ocean adds movement, vibration, temperature gradients, and unpredictable stress patterns that the chambers cannot replicate. Temperature plays a significant role in early failures as well. Batteries that run well in laboratory conditions behave differently at near-freezing temperatures. Chemical reactions slow, leading to reduced power output. Lubricants thicken, causing motors to stall. O-rings and seals stiffen, creating gaps where water can intrude. Electronics drift from their intended performance ranges. Cables become brittle. Connectors lose flexibility. Many devices intended for deep water fail during cold testing well before they are tested for pressure. When engineers attempt to balance cold resilience with pressure resistance, the list of workable materials shrinks even further. Machines that survive both pressure and temperature testing still face difficulties when placed in open water. The moment a device enters the ocean, new variables appear. Currents move it. Salinity interacts with materials differently than pure test water. Small vibrations from ship engines or deployment cables travel through the structure. At mid-depths, variable density layers affect buoyancy and descent rates. Estimating how a device will descend is essential. If it sinks too quickly, the structural load increases abruptly. If it sinks too slowly, the mission may run out of time or power. Failure in these early deployments often comes in the form of cracks, water ingress, communication interruptions, or difficulties maintaining orientation. Communication failure is one of the most common issues. Most deep-sea vehicles rely on acoustic signals that must travel through thousands of meters of dense water, bouncing through layers with different temperatures and densities. These layers bend or scatter signals, causing delays, signal loss, or distorted commands. Sometimes a vehicle cannot be located after deployment. Sometimes it cannot receive the command to release its ballast and rise to the surface. These failures often result in the loss of the entire machine. When a device disappears into the trench, recovery is unlikely. The depth makes retrieval extremely difficult, and the area is vast. Some machines fail because the descent is too rough. The water column above the trench is not uniform. There are turbulent zones, unexpected currents, and pockets of varying density. These cause drag or uneven forces on different parts of the structure. A machine built to descend calmly can experience unexpected jolts or oscillations. These vibrations, harmless at shallow depths, become dangerous deeper down. They stress joints, loosen components, and compromise seals. By the time the device reaches the deeper zones, it may already be weakened. For remotely operated vehicles, tether cables introduce additional points of failure. The cable must be strong enough to withstand currents and the vehicle's weight, yet flexible enough to allow maneuvering. At extreme depths, these cables can stretch, twist, or accumulate tension in ways that affect vehicle control. If a cable snaps under tension, the vehicle is lost instantly. Even when it doesn't snap, performance can deteriorate as the cable drags or shifts unpredictably. Engineers often discover these limitations only during sea trials, causing the machine to fail operationally despite surviving basic structural tests. Autonomous landers, which rely on pre-programmed instructions and free-fall descent, face their own challenges. They must be heavy enough to sink, yet buoyant enough to return. Their release mechanisms must function flawlessly, despite cold, pressure, and mechanical stress. If a release mechanism jams, the lander becomes permanent seafloor debris. If a buoyancy system malfunctions, it rises too fast or too slowly, risking damage. Many early designs failed due to simple mechanical sticking points that became magnified under deep-sea conditions. Buoyancy failure is another frequent issue. Engineers use syntactic foam to provide lift, but even the best foam compresses at depth. Compression reduces buoyancy. Reduced buoyancy means the machine may not ascend after its mission. Machines lost in this way often worked perfectly during descent and operation, but could not return to the surface. This is one of the most frustrating forms of failure because the machine might have gathered valuable data. Yet without retrieval, the data is not accessible. Some devices fail simply because of the seafloor's unpredictability. The bottom of the Kermadec Trench is not smooth. It contains soft sediments, steep slopes, jagged rocks, and shifting ground. A machine landing on an incline may topple. A sampling device may sink too deeply into soft sediment and get stuck. Instruments may tilt, compromising measurements. Even if the machine is strong enough to survive the descent, the landing environment can undermine the mission before any scientific work begins. Even the descent line used for some instruments can fail. Lines stretch under load, knots tighten or loosen, connectors corrode. Mechanical stress accumulates over time. Many devices disappear due to minor issues in these components. A single weak link can cause the entire system to fall away into the trench without control. The logistics of deployment also create opportunities for failure. The trench is remote, and research ships must travel long distances to reach it. These journeys expose equipment to storms, humidity, salt spray, and vibration. Crates shift. Tools suffer corrosion. Instruments encounter wear before they even enter the water. Some machines arrive on site already compromised. Engineers discover leaks, misalignments, or damaged sensors only when preparing for deployment. Sometimes the faults are fixable. Sometimes they end the mission early. The cost of these machines magnifies the consequences of failure. Each loss represents not only financial investment but months or years of planning, construction and testing. It also represents lost scientific opportunity, as each destroyed or lost machine takes its data and samples with it. This makes engineers cautious. They design conservatively. They limit risk. They avoid experimental configurations unless absolutely necessary. But caution alone cannot overcome the environment's demands. Even conservative designs fail when the trench pushes them beyond their limits. This pattern creates a cycle. Engineers build machines. They test them. They lose some. They refine the next generation. They succeed occasionally. They fail often. Each failure teaches something new about the conditions, the materials, or the design. But the trench remains ahead of us, always demanding more resilience, more precision, more understanding. This is why so few machines ever touch the deepest parts of the Kermadec Trench. It's not because we lack interest or ambition. It's because reaching this place requires a machine that survives pressure, darkness, cold, unpredictable currents, acoustic distortions, seafloor instability, and extended isolation. Most machines don't even get past the early steps. They fail in workshops, pressure chambers, test pools, or during first deployment trials. They fail because the trench environment punishes any imperfection, any oversight, any compromise in design. As the exploration continues and research efforts persist, the focus shifts from understanding why machines fail to how we can build systems that endure long enough to gather data. And from there, the story moves into the complications introduced by the trench's sheer physical force, the way cold changes every material, and how the shifting seafloor creates challenges that require engineering solutions far beyond what most deep-sea missions face. Reaching the depths of the Kermadec Trench forces engineers to confront a truth that becomes clearer the deeper they try to go. There are very few materials on Earth that behave predictably under extreme pressure, and even fewer that survive long enough to perform meaningful work. When people imagine deep-sea exploration, they often picture strong metals, advanced composites, or futuristic ceramics standing firm against the weight of the ocean. In reality, Most materials that perform flawlessly at the surface begin to misbehave far earlier than expected. They bend, compress, crack, deform, fatigue, or fail outright. And the deeper the descent, the more the ocean magnifies even the smallest weakness, turning what would be a minor inconvenience in shallow water into a mission-ending structural collapse. The weight involved is not metaphorical. It is literal and unavoidable. Pressure increases steadily with depth, adding roughly 1 atmosphere, about 14.7 pounds per square inch, for every 10 metres of descent. At the bottom of the Kermadec Trench, that amounts to more than 1,000 atmospheres pressing down from every direction. Materials don't simply endure this load. They must maintain their structural integrity while being pushed evenly across every surface, seam, joint, and connection. If a material isn't perfectly suited to this environment, the pressure will exploit the floor. And it never stops. The load remains constant for as long as the machine is down there. Steel is often the first material people think of when imagining deep-sea structures. But steel reveals its limits quickly in extreme depths. Standard steel plates weaken under long-term compression. Even high-grade steel, which holds up well in mid-depth operations, experiences micro-cracking at trench depths. The ocean slowly forces its way into tiny imperfections, turning them into points of stress concentration. Welds become vulnerable, corners deform. Over time, the steel either bends or splits under the relentless load. Steel's weight also makes it difficult to use in a full-depth craft because heavier materials require more buoyancy support. The moment engineers attempt to compensate with additional syntactic foam, the foam's compression limits introduce their own problems. Every trade-off spirals into another. Aluminum performs no better. It's lighter than steel, making it attractive for mid-depth vehicles, but it lacks the strength needed for deep trenches. Aluminum crushes under heavy loads, and while engineers can thicken aluminum hulls to add strength, doing so increases weight to unacceptable levels. That added weight demands more syntactic foam, which compresses and reduces buoyancy at depth. The entire design becomes unstable. Most deep-sea engineers dismiss aluminum early in the planning stages because it cannot maintain both strength and lightness at the scale required for trench exploration. Titanium stands out as the strongest widely usable metal for extreme depth work, but titanium is not a perfect solution. It resists corrosion and maintains strength better than steel or aluminum, yet it comes with difficulties of its own. Titanium is expensive, hard to machine, and sensitive to manufacturing flaws. A hull made from titanium must be shaped with precision. Even the slightest deviation from a perfect sphere creates uneven stress distribution. In trenches, uneven stress quickly becomes catastrophic stress. A weld made with a minor impurity or misalignment can crack when compressed from all directions. Once a crack starts, it grows quickly under constant load. Titanium also becomes brittle in certain temperature ranges, and near-freezing trench waters push materials into that brittle zone. Engineers know this, and must design around it, adding complexity and cost. Ceramics offer impressive pressure resistance. They don't deform easily and can withstand loads that would crush metals. But ceramics crack without warning. Under trench conditions, a ceramic housing that appears flawless can fail suddenly if exposed to a small impact, a minor manufacturing defect, or a temperature shift. Once a crack begins, the ceramic shatters instantly. This lack of gradual failure makes ceramics dangerous to rely on for primary pressure resistance. They may work in small components such as pressure-protected camera housings or instrument windows, but they are too unpredictable for larger structures. Glass has a long history in deep-sea observation, but glass only works within certain depth limits. Thick acrylic domes or viewing ports can handle moderate pressure, but not the full weight of the Kermadec Trench. Even specialised borosilicate glass or fused quartz structures reach their failure points far above trench depth. Glass suffers from stress concentration around imperfections, and under high compression, tiny flaws become catastrophic cracks. That's why full-depth submersibles avoid windows entirely. Instead, they rely on cameras, which introduce their own material challenges. Plastics, even advanced engineering plastics, simply aren't suited for extreme depths unless they're part of pressure balance systems. Under high compression, plastics deform permanently. They lose shape, crack, or creep over time. While some plastics work well for insulation, cables, or gaskets, none serve as primary structural components. When engineers use plastics in deep-sea craft, those plastics must operate in pressure-compensated environments where the internal pressure matches the external load, or where the plastic is housed within a stronger material. Composites, materials combining fibres and resins, offer interesting possibilities. Carbon fibre, for example, has remarkable strength in tension, but far less strength in compression. The Kermadec Trench doesn't stretch materials, it squeezes them. Carbon fibre layers buckle under compression, delaminate, and collapse. Fibre-reinforced composites behave similarly. Their strength relies on fibres resisting tension, but the ocean applies pressure from every direction, pushing materials inward rather than pulling outward. Engineers continue to experiment with composites, but no composite structure has yet proven consistently reliable at trench depths. Even syntactic foam, one of the most essential materials for deep exploration, has limits. Syntactic foam consists of hollow microspheres embedded in resin. These microspheres resist compression individually, and the foam as a whole provides buoyancy without collapsing. But at trench depth, even the microspheres compress. The foam loses volume. As the foam shrinks, it provides less lift. A vehicle that relies too heavily on syntactic foam may rise slowly, rise unpredictably, or fail to rise at all. Engineers must carefully calculate how much compression will occur, but slight miscalculations lead to disastrous outcomes. Many early deep-sea landers never returned to the surface because their buoyancy materials compressed too much to overcome their own weight. Pressure-balanced oil-filled systems offer another strategy. Instead of protecting electronics from pressure with rigid housings, engineers immerse them in incompressible oil so that the internal pressure matches the external load. This approach prevents crushing, but creates other issues. Oil expands and contracts with temperature. Seals must be absolutely perfect. Any water intrusion into oil ruins the electronics. Connectors must work reliably while submerged and pressurized. Oil-filled designs work for some sensors or cameras, but introduce heavy maintenance requirements and remain vulnerable to long-term exposure. Pressure affects not only structural components but also fasteners, seals, cables, and coatings. Bolts that hold firm at the surface bend or break when compressed. Gaskets stiffen and lose flexibility, creating leaks. Rubber seals shrink. Adhesives become brittle. Coatings designed to resist corrosion degrade under combined pressure and cold. Even materials considered deep-sea safe may behave unpredictably under conditions unique to the trench. Corrosion becomes another major factor. The deep ocean is cold, oxygen-poor and chemically distinctive. High pressure accelerates certain chemical reactions. Metals that resist corrosion at the surface may corrode more quickly at depth, especially when surfaces experience micro-cracking that allows seawater to enter. Galvanic corrosion, when two dissimilar metals interact electrically, intensifies under pressure. Engineers must carefully select compatible metals, avoid unnecessary contact between materials, and design protective measures that remain effective despite temperature and pressure extremes. Cabling introduces its own complications. Insulation materials must resist both pressure and cold. At extreme depth, seawater presses into cable jackets, forcing itself between layers. Over time, water infiltration causes electrical shorts. Cables become stiff and brittle. Connectors fail due to differential compression between insulating materials and metal components. Deep-sea vehicles often fail not because of hull issues, but because of cable damage caused by extreme pressure and temperature. Even coatings, often overlooked, fail under trench conditions. Anti-corrosion coatings crack. Paints peel or separate from metal surfaces. Pressure forces water into microscopic gaps between coatings and the underlying material. Once water is trapped there, it causes blisters or delamination. Engineers must select coatings specifically designed for extreme depths, but even the best options degrade over time. The combination of pressure and cold worsens every failure mode. Materials that become brittle in cold temperatures fracture more easily. Lubricants thicken, causing motors and moving parts to stall. Bearings seize, actuators lose force. Engineers try to use specialized deep-sea lubricants, but even these become sluggish near freezing. Any moving part must be designed to operate with minimal friction and enough tolerance to avoid binding, yet tight enough to prevent water intrusion. One of the most difficult challenges is designing joints and interfaces. Even if a hull is strong enough, any opening, such as a hatch, window, sensor port or cable entry point, becomes a vulnerability. Pressure concentrates around edges. Seals must maintain integrity under both compression and temperature shifts. A joint that tolerates cold but not pressure will fail. A joint that tolerates pressure but not cold will also fail. Engineers must strike a balance that allows both extremes, and this balance is not easy to achieve. Sampling tools also suffer from material issues. Arms designed to pick up rocks bend. Scoops deform. Container lids jam under pressure. Springs behave differently. Hinges freeze. Even if a sampler reaches the seafloor intact, it may not function when it gets there. Countless missions have returned empty-handed not because the sampler broke during descent, but because its components behaved unpredictably in the trench. The ocean's weight even affects how materials age. Exposure to high pressure changes internal structures. Metals become work-hardened in ways that weaken them. Composites develop internal delamination. Plastics retain subtle deformation that alters their fit. O-rings compress permanently. Syntactic foam loses volume permanently. A vehicle that survives one trench dive may not survive a second without extensive inspection and repair. Deep-sea vehicles are not mass-produced machines. Each dive stresses them near their limits. All of these factors combine to explain why exploration of the Kermadec Trench remains so limited. It is not enough to design a vessel that reaches depth once. It must reach depth, perform scientific tasks, handle unpredictable conditions, and return safely carrying valuable data. Most materials cannot handle this sequence. They buckle under load, crack under cold, or deform under long-term exposure. The harsh environment exposes every weakness. This is why engineers treat trenches as proving grounds, places that reveal whether materials behave as expected or hide flaws that surface only under extreme conditions. Every failed mission teaches something new about how materials respond. Every successful mission relies on thousands of hours spent testing, refining, and re-engineering components. And even with all of this, the Kermadec Trench continues to push the limits. From here, the story moves naturally toward the next unavoidable challenge: the deep ocean's cold, the way near-freezing temperatures interfere with power systems, electronics, biological activity, and mechanical reliability. Cold alone would be manageable. Pressure alone would be manageable. But in the trench, they come together, creating an environment where both must be addressed simultaneously. And that combination reshapes everything we try to send into the depths. Descending toward the Kermadec Trench means entering a realm where temperature becomes as decisive and unyielding as pressure. If the crushing force of the ocean shapes what materials we can use, the cold strips away whatever resilience remains. Near the surface, the ocean can be warm, sometimes comfortably so. But the deeper you go, the more that warmth disappears. It doesn't fade the way sunlight does. It drops sharply, relentlessly, and predictably until it reaches a point where water hovers just above freezing. That cold extends across every corner of the trench. It does not fluctuate with seasons. It does not respond to the sun. It is constant and unbroken, a defining feature that reshapes machinery, slows chemical reactions, and imposes limits on what can function at all. The cold at these depths sits between 4°C and 2°C, depending on location and current. That might sound manageable. After all, people store electronics in cold rooms, operate machines in the Arctic, and design equipment that functions in space, where temperatures drop far lower. But the deep ocean does not behave like cold air or the vacuum of space. Water withdraws heat faster than air. It strips warmth with an efficiency that leaves no room for gradual adjustment. Anything warm becomes cold quickly. Anything relying on internal heat must fight constantly to retain it. Any system requiring steady thermal conditions finds those conditions slipping beneath it. Every material and component reacts to this cold differently. Metals contract, plastics stiffen, lubricants thicken, electronics drift outside their ideal operating ranges, batteries lose efficiency, gaskets that remained flexible during pressure testing become rigid, sensors lose accuracy, adhesives weaken, even light behaves differently, with LEDs dimming slightly and some high-intensity lamps struggling to remain stable. This cold bends the rules of engineering, turning reliable systems into unpredictable ones, and when combined with the extreme pressure, the results often surprise even experienced designers. One of the most significant challenges is battery performance. Most deep-sea machines rely on battery power. There is no sunlight to collect, no wind to capture, no way to run cables 10,000 meters down without risking entanglement, fracture, or excessive drag. Batteries, however, behave worst in cold temperatures. Chemical reactions slow dramatically. Capacity shrinks. Voltage drops. A battery that lasts 10 hours in a laboratory might last only 3 at depth. Engineers attempt to compensate with insulation, but insulation does not halt the cold. It only delays it. Eventually, the battery's temperature drops close to the surrounding water, and its performance collapses. High-pressure housings add another complication because thick metal walls conduct cold inward even faster. Some missions use heated enclosures to keep electronics warm, but heating consumes precious power. The moment heat spreads outward, the surrounding water absorbs it. The system must replenish that warmth constantly, draining the battery faster. This creates a problem with no ideal solution. Without heat, electronics drift. With heat, power drains. Engineers must balance power consumption carefully, deciding how much energy to devote to science instruments and how much must be reserved for temperature control. Even components that don't require electricity face cold-related issues. Lubricants designed for high-pressure environments become thick and sluggish near freezing. Motors that run perfectly in test tanks suddenly stall. Gears move slowly, scraping or grinding as their lubricant turns into something close to paste. Under pressure, this thickening becomes more pronounced. Engineers often switch to specialized deep-sea lubricants, but these are expensive, difficult to produce, and still not immune to cold-induced stiffening. Moving parts, arms, clamps, hinges, pumps, must be designed with increased tolerances to avoid seizing. But increased tolerances reduce precision. A sampling arm built to withstand cold must sacrifice finesse. A pump built to handle thick lubricants may lose efficiency. Every adjustment made to account for cold reshapes the machine's capabilities. O-rings and seals perform even worse. These small components sit at the boundary between machinery and seawater, making them among the most critical points of failure. In cold temperatures, O-rings lose elasticity. They no longer flex to maintain a tight seal. Instead, they shrink slightly, stiffen, and in doing so allow microscopic gaps. Under shallow water conditions, such gaps might cause slow leaks. In a trench, those gaps allow immediate intrusion of high-pressure seawater. Many early deep-sea attempts failed because a single seal stiffened too much during descent. letting water in and destroying everything inside. Engineers now choose materials specifically rated for deep-sea cold, but even those materials experience changes in elasticity over time. Cables also react poorly to extreme cold. Their insulation becomes brittle, developing cracks when flexed. Electrical resistance changes. Connectors stiffen. These issues alone would be manageable, but under extreme pressure, the cold pushes cables into failure-prone states. Small cracks become entry points for water. Once water reaches the copper inside, corrosion begins rapidly, even in cold conditions. Electrical shorts follow. In many missions that lose contact with their vehicles, the root cause is a cold stiffened cable failing under tension or pressure. The cold affects sensors in subtle ways. Chemical sensors become sluggish. Optical sensors need more power to maintain brightness. Sound sensors pick up more noise from temperature-induced material contractions. Even pressure sensors, meant to measure the very environment causing the problem, experience calibration drifts. These drifts make data unreliable unless corrected through models built from previous missions. But since missions are limited and data sparse, those models often rely on assumptions. Every new dive must confirm or adjust those assumptions, and the cold almost always complicates this process. This temperature also affects adhesives and coatings. Adhesives used to secure components inside housings lose flexibility. They become brittle, making them more likely to crack under vibration or pressure. Coatings that protect against corrosion sometimes separate from surfaces when they contract, allowing seawater to creep beneath them and accelerate degradation. These failures may not destroy the machine immediately, but they weaken it for future missions. Deep-sea vehicles rarely last long because each dive inflicts invisible damage that accumulates. The cold contributes heavily to this gradual deterioration. Perhaps the most unexpected effect of deep-sea cold is its influence on fluids. In typical conditions, fluids behave predictably. They flow at certain rates, respond to pressure in known ways, and maintain their consistency. But in trench conditions, fluids thicken or stratify. In battery packs, electrolytes grow sluggish. In hydraulic systems, fluid movement slows, reducing response times. In pressure compensation systems, the balance between internal and external fluid becomes delicate. If a compensating fluid cools too quickly, its contraction may create pressure differences that cause housings to collapse inward. Engineers must account for this contraction by designing reservoirs or expansion bladders. But these components are themselves subject to cold-induced stiffening, creating a cycle of interdependent failures. Computers and processors behave differently as well. While some electronics operate better at lower temperatures due to reduced thermal noise, deep-sea cold drops below optimal performance ranges. Microprocessors slow slightly. Timing systems drift. Memory chips become more prone to error. These effects are minimal in mild cold but significant in near-freezing water for extended periods. This drift forces software engineers to design systems capable of correcting or absorbing these irregularities. Even those systems can fail when electronics reach temperatures lower than they were ever designed to withstand. The cold also intersects with pressure to create unique challenges. In pressure chambers on land, engineers simulate high pressure or low temperature, but rarely both at once to full trench conditions. Testing both simultaneously is expensive and technically difficult. As a result, some failures only appear in the real environment, where the cold accelerates pressure-based issues. A material that survives pressure testing at room temperature may behave differently at near-freezing levels. Likewise, a system that works in cold air may not handle cold under compression. The combination reveals weaknesses that neither condition alone would expose. These deep-sea temperatures also slow biological processes, which affects how organic materials behave. Biological samples degrade more slowly, but microbial activity on equipment surfaces persists. Biofouling, a buildup of microorganisms, can occur even at depth. While much less aggressive than surface-level biofouling, it still affects sensors over time. But because the cold slows biological growth, it also slows chemical reactions that might otherwise help sensors detect certain environmental compounds. In this way, the cold reduces sensor efficiency. The trench environment doesn't damage sensors through heat or corrosion. It simply slows the underlying chemistry until the sensor cannot respond adequately. Even instruments designed to measure temperature struggle. Their readings must be corrected for the cold's effect on their own internal components. The margin of error increases. Some temperature sensors drift enough that readings from one mission cannot reliably be compared to readings from another without recalibration. This creates gaps in long-term monitoring. Another challenge emerges when trying to maintain machinery temperature across long missions. Deep-sea missions can last hours or days. During that time, machines cool steadily until reaching equilibrium with the surrounding water. Engineers must design systems that tolerate this inevitable cooling. Heating everything is impossible due to energy limits. Instead, they isolate critical components, wrap them in insulation, or use specialized housings. But no insulation prevents eventual cold encroachment. It can only slow it. Even ascent back to the surface is complicated by cold. As a machine rises, it moves through temperature gradients. Components expand again. Materials that were compressed and rigid begin to loosen. Differential expansion can create new stresses. A connector that remained sealed at depth may loosen at mid-depth. A brittle cable may crack as it warms. A battery that operated poorly in the cold may suddenly surge in output as temperatures rise. Engineers must design systems that can survive not just the deepest environment, but also the transition back to warmer conditions. The cold also complicates sample collection. Biological samples kept at ambient trench temperature must be preserved immediately. Otherwise, they warm during ascent and degrade rapidly, losing the unique chemical states they had at depth. Some missions use pressure-retaining containers to store samples at depth conditions throughout the return. But these containers are difficult to design. They must withstand extreme pressure while preventing warming. A slight increase in temperature can destroy data on protein structure, metabolic activity, or cell membrane composition. As a result, capturing useful biological samples from the trench is one of the most challenging goals in deep-sea research. Geological samples are easier to preserve, but even they face issues. Cold sediment solidifies and adheres to sampling tools. If tools warm during ascent, the sediment changes texture. Water trapped inside samples expands or contracts. Gases form bubbles. All of these changes alter the sample's original state. Scientists must account for these transformations when analysing their results, layering correction models onto every measurement. Because the cold changes everything it touches, engineers treat trench exploration as a matter of endurance. Machines must endure the cold long enough to carry out tasks, record data, and return. Most machines fail not because they can't reach the trench, but because they can't function long enough once they arrive. Electronics lose reliability. Moving parts seize, batteries fade, sensors drift. The cold chips away at a vehicle's capability until little remains operational. These limitations explain why deep-sea missions rely heavily on simplistic designs. Complex systems fail more easily. Simpler systems have fewer points of weakness. Many trench vehicles consist of straightforward frames carrying a few sensors, lights, and cameras. They lack the intricate manipulators, advanced propulsion systems, or sophisticated robotics seen in shallow water vehicles. Complexity and cold rarely mix well. This harsh environment also slows scientific progress. Each mission gathers limited data. Machines must be rebuilt or repaired extensively after each dive. Engineers must analyse which components failed due to cold, redesign them, test them again, and hope the next dive reveals fewer weaknesses. It transforms exploration into a slow, stepwise process, with each success carved out through iteration. Understanding the cold helps explain why the Kermadec Trench remains out of reach. Even if pressure-resistant materials existed in abundance, even if communications were perfect, Even if darkness posed no barrier, the cold alone would still threaten every mission. It is as constant as pressure, as unchanging as darkness, and as unavoidable as the depth itself. And yet this cold is only one part of a larger system. Beyond the temperature and pressure, the seafloor beneath the trench is alive with movement. The landscape shifts, settles, and rearranges itself under tectonic forces. Machines built to withstand cold and pressure may still face failure when they encounter a ground that does not remain still. In the next step of this journey, the focus turns to the unstable terrain, how it moves, how it changes, and how it reshapes every attempt to touch the bottom of the Kermadec Trench. The seafloor near the Kermadec Trench does not behave the way people imagine the deep ocean might. Many picture the bottom as a silent, undisturbed plain where nothing moves and nothing interrupts the stillness. The reality is almost the opposite. The ground beneath the trench is shaped by continuous motion, slow rearrangements, sudden shifts, and long-term cycles driven by forces deep within the earth. These movements don't resemble the dramatic earthquakes shown in documentaries. They're often subtle, often invisible, and often spread across vast stretches of sea floor. But even the smallest shift becomes a major obstacle when we try to explore the trench with machines that depend on stability. The result is a landscape that defies simple mapping, a world that refuses to stay still long enough for instruments to capture it accurately. The Kermadec Trench sits at a boundary where the Pacific Plate slides beneath the Indo-Australian Plate. This process, known as subduction, is one of the most powerful geological interactions on Earth. It operates at speeds so slow that they sound harmless, mere centimetres per year, but that movement builds an environment full of tension, compression, uplift, collapse, and deformation. When one tectonic plate dives beneath another, the downward movement doesn't just create depth, it creates a complex topography of sharp slopes, deep valleys, unstable cliffs, and rolling sediment. These features change over time. They adjust to shifts in the plates, to bursts of seismic activity, to underwater landslides, and to the steady accumulation of loose material drifting down from above. Because the trench is a product of plate motion, it never reaches a final form. It's an environment constantly under construction. This is why maps of the Kermadec region often show smooth approximations rather than detailed relief. Sonar and satellite altimetry can detect broad features, but not fine ones. Even when sonar provides high-resolution data, that map becomes outdated quickly because the seafloor shifts in ways we cannot predict or monitor continuously. Much of the instability comes from sediment. The trench walls gather huge amounts of loose material, particles, sand, mud, organic fragments that drift down from upper ocean layers. Over thousands of years, this material builds up into massive deposits resting on steep inclines. These deposits may sit undisturbed for long periods before suddenly sliding downward under their own weight. Such slides can be small and gradual or large and abrupt. A major slide can reshape hundreds of meters of terrain, burying rocks, exposing new surfaces, and forming deep channels cut through sediment layers. Any machine resting on that slope risks sinking into soft material or toppling as the ground shifts under it. Even without landslides, the seafloor experiences creep. Slow downward movement of sediment under gravity. This creeping causes surfaces to tilt, flatten, or fracture. A lander placed on what appears to be a stable surface may begin to lean gradually as the ground beneath it shifts. Cameras mounted on the lander record the tilt as small, steady changes in orientation. Over hours, the tilt grows until instruments no longer point where they should. Over days, the lander might slide into a depression or become partially buried. Once this happens, recovery becomes difficult and often impossible. Some parts of the trench floor consist of exposed bedrock shaped by tectonic movement. These rock surfaces may appear more stable, but they come with their own challenges. They form irregular ridges, sharp edges, and slopes far steeper than expected. An autonomous vehicle navigating these zones must rely on sonar to detect edges and avoid collisions. But sonar resolution decreases with depth, and the extreme pressure distorts sound propagation, making it difficult to identify slopes accurately. As a result, vehicles risk colliding with unseen outcrops or hovering above terrain they cannot map properly. Another challenge emerges from the trench's occasional seismic activity. The Kermadec region is one of the most active tectonic zones on the planet. Earthquakes occur frequently, ranging from small tremors to major events, powerful enough to reshape seafloor features across wide areas. These earthquakes cause shifting sediment, cracking rocks, tilting surfaces, and reorganizing channel networks in the trench. Machines deployed during these events may be damaged or lost, but even if they survive, the data they collect becomes harder to interpret because the environment changes faster than expected. The trench also experiences submarine faulting, fractures where seafloor blocks move relative to each other. Some areas rise slightly while others sink. Fault lines create elevated ridges and deep depressions. These features shift over time due to cumulative tectonic force. Instruments placed near fault zones may end up far from their original positions after multiple small movements. If a device attempts to land near a depression, even a tiny shift in the ground might cause it to fall downward unexpectedly. Because these movements occur slowly compared to a human timescale, they are difficult to measure in real time, yet they matter tremendously to the durability and reliability of machines sent into the trench. Water also plays a role in reshaping the landscape. Deep ocean currents, though weak compared to surface currents, still drag sediment across the ocean floor. Over long periods, these currents carve channels or smooth edges. They also create pockets of instability, where loose material accumulates. These pockets can collapse without warning when a machine disturbs them. A lander positioned directly on such a spot may sink by several centimetres, or in some cases several meters, compromising the levelness required for accurate measurements. Mapping such a dynamic landscape requires multiple approaches. Satellite altimetry provides broad outlines but cannot resolve the fine structure, because satellite measurements cannot penetrate the ocean's surface. Ship-based sonar can map shallower regions but loses resolution at extreme depths. High-frequency sonar, which produces detailed maps, cannot reach the trench floor effectively because water absorbs these frequencies too quickly. Low-frequency sonar penetrates deeper but provides coarse images. Engineers and scientists must stitch together partial, blurry maps to estimate the general shape of the seafloor, fully aware that many of the details may already be inaccurate by the time they are published. Remotely operated vehicles and autonomous underwater vehicles can map small sections with high precision, but these missions cover only tiny fractions of the trench. They also risk damage when navigating slopes or unstable zones. After a few deployments, these vehicles begin to show wear from pressure, cold, and terrain interaction. As a result, detailed mapping remains rare and incomplete. Even when detailed data exists, it often lacks broader context because the region is simply too large to survey comprehensively. The absence of reliable maps affects every stage of exploration. Engineers must design descent paths without knowing exactly what terrain lies beneath. They must plan landing sites based on limited or outdated information. They must accept that vehicles may encounter unexpected slopes, ridges, or loose sediments. Even choosing a safe location to drop a lander becomes difficult, and because each dive is costly and risky, scientists cannot simply send dozens of vehicles to scout for suitable zones. Instead, they choose a few locations based on the best available models, aware that those models may miss key features. The unpredictable terrain also affects sample collection. Geological samples require stable placement of arms or scoops, but shifting sediment can cause a sampling arm to miss its target or collapse into softer ground. Biological samples can be lost if a vehicle kicks up sediment or drifts into a slope. Instruments intended to measure chemical conditions may be compromised if they land on a surface that continues to move during the measurement period. Even measuring seafloor temperature becomes difficult if sensors sink unevenly into sediment, altering their exposure. Some missions attempt to anchor equipment into the seafloor, but anchoring in a shifting environment is unreliable. Anchors sink too deeply into soft sediment or fail to grip on smooth rock. The seafloor's inconsistencies make any anchoring strategy risky. Strategically placed equipment might tilt over time, affecting readings. If the seafloor shifts significantly, anchored equipment might detach or become damaged. Even if engineers could overcome these issues, mapping itself presents other technical challenges. Navigation at extreme depth relies on acoustic signals that distort as they pass through temperature and density layers. Vehicles cannot rely on GPS because GPS signals do not penetrate water. Instead, they depend on acoustic beacons, inertial navigation systems, or long baseline positioning systems. Each of these systems introduces its own inaccuracies. Acoustic beacons drift. Inertial systems accumulate error over time. Long baseline networks require precise placement of multiple underwater receivers, an impossible task in a landscape that keeps shifting. The result is that even when vehicles attempt precise mapping, their positional uncertainty often grows larger than the features they are trying to measure. Because of the difficulties in mapping, scientists studying the trench rely heavily on indirect methods. These include seismic readings, water column chemistry, and models based on plate tectonics. Seismic readings can reveal the location of fault lines or the depth of the subducting plate, but they do not show surface features clearly. Chemical signals can indicate the presence of hydrothermal vents or areas of active geological change, but they cannot pinpoint exact locations without visual confirmation. Tectonic models predict long-term changes in the trench's shape, but cannot account for small, rapid shifts in sediment. The consequence of all this is that the Kermadec Trench remains one of the least mapped deep-sea environments on Earth. While other trenches, like the Mariana, have received more attention and thus more surveys, the Kermadec's remoteness and instability keep it largely unmapped. Scientists know its general shape and depth. They have small patches of high-resolution maps from specific missions, but broad regions remain unknown. The phrase unexplored frontier applies literally here, not metaphorically. Even when machines attempt photogrammetric mapping, using hundreds of overlapping photos to build a 3D model, they encounter problems. The darkness limits visibility to only a few meters. The cold affects camera function. The pressure distorts lenses and light housings. Sediment clouds form easily when a vehicle approaches too close to the seafloor, ruining visibility. These photos often reveal only small, isolated patches of terrain. Stitching them into large models becomes nearly impossible, because relative positions are difficult to determine without accurate navigation. Another factor is the unexpected presence of biological structures. Burrowing organisms create small mounds and depressions. Some species form fragile tube structures or microbial mats. These features can confuse mapping systems, causing false identifications of geological formations. When machines pass through these areas, they may damage the biological structures unintentionally, altering the environment they intend to study. All these challenges feed into the larger difficulty of reaching a clear understanding of the trench. Even experienced researchers cannot predict how the ground will behave during a mission. The landscape might shift between dives, making repeated observations of the same area problematic. A feature recorded during one mission may look different in the next. Some structures disappear, buried by sediment. Others appear suddenly due to small slumps or rockfalls. Without a stable reference, long-term studies become harder to conduct. Because mapping is so limited, we still have more questions than answers about the trench floor. We don't know where all the vents are. We don't know how sediment moves over decades. We don't know what processes create specific formations. We don't know how often landslides occur or how far they travel. We don't know how biological communities adapt to this constantly shifting terrain, and each unknown influences how machines must be designed. This constant movement means that any comprehensive mapping effort would require technology capable of maintaining stable navigation, precise imaging, reliable long-term power, and resilience to pressure, darkness, and cold. Machines would need to operate longer than anything we currently deploy. They would need to withstand environmental stress without losing position, clarity, or functionality. Such machines do not yet exist. The landscape itself remains the final obstacle before reaching the biological mysteries that lie deeper in the trench. Only after accounting for the shifting Earth can we begin to understand the creatures living there and the ways in which the environment shapes their evolution, behaviour, and survival. Life in the Kermadec Trench does not resemble the life we recognise near the surface. It doesn't behave the same way, grow the same way, or rely on the same rules. It evolves under a set of demands that would overwhelm nearly every known organism: relentless pressure, near-freezing temperatures, complete darkness, scarce food, unpredictable terrain, and isolation from the rest of the biosphere. These conditions strip biology down to its most essential forms. Anything unnecessary is discarded. Anything fragile is eliminated. Anything inefficient is weeded out. What remains is life built specifically for the impossible, shaped not by abundance or sunlight or stability, but by constraints that force evolution into directions most species will never encounter. When people imagine deep-sea creatures, they often picture glowing fish, bizarre shapes, fanged predators, or translucent bodies floating through the dark. The reality of the trench floor is far more restrained. It isn't a world of giant monsters or cinematic creatures. Instead, it's a world built around minimalism. Most inhabitants are small, slow, flexible, and physically simple. Their bodies follow principles that allow survival in a place where every movement consumes precious energy. The resources here are limited. Food arrives sporadically. Temperatures remain low enough to slow biochemical reactions. Pressure is constant and crushing. In this environment, flashy adaptations are luxuries nature cannot afford. Instead, the trench hosts organisms that succeed because they are unremarkable in one sense and extraordinary in another. Their entire physiology is tuned to withstand conditions that would destroy familiar species instantly. The first thing to understand about trench life is that bones are rare. Hard structures collapse under extreme pressure. Calcium-based skeletons cannot maintain integrity at depth, because the pressure acting on them is not simply downward. It presses in from all sides. Hollow spaces within bone, which work well on land or in shallow water, become points of weakness. As pressure increases, these spaces cannot remain stable. That is why the majority of animals living at full trench depth have soft bodies. Their tissues compress slightly but do not crack. Their shapes conform to pressure instead of resisting it. These organisms don't battle the environment, they match it. Many animals in the trench fall into two broad categories: benthic creatures living on or in the seafloor, and pelagic creatures drifting just above it. Benthic organisms include small fish, amphipods, holothurians, sea cucumbers, and polychaeta worms. Pelagic organisms include gelatinous animals, ghostly fish, and small crustaceans adapted to drifting rather than active swimming. Each group has evolved unique strategies to conserve energy and survive in long periods without food. Fish are not entirely absent at these depths, but they appear in fewer numbers and with more limited diversity. The deepest living fish recorded on Earth belong to the snailfish family, found in trenches across the Pacific. Although the deepest confirmed snailfish sightings come from the Mariana Trench, related species likely inhabit the Kermadec's extreme depths as well. These fish do not resemble typical shallow water species. They lack scales, have soft gelatinous bodies, and possess thin, flexible bones. Their muscles contain special compounds that maintain fluidity under pressure. Their internal chemistry includes molecules that act like antifreeze, preventing proteins from deforming in the cold. Their skin is translucent because pigmentation offers no advantage in a world without light. Their bodies appear fragile, yet they are perfectly suited to deep-sea conditions. Snailfish feed primarily on small crustaceans such as amphipods. Amphipods thrive in trenches because they tolerate pressure extremely well and have specialised cell membranes built to remain functional under compression. Some amphipod species in the trench reach sizes larger than their shallow water relatives. This phenomenon, known as deep-sea gigantism, appears in various trench organisms. The exact reason remains debated, but possibilities include cold temperatures slowing metabolism, low oxygen levels selecting for more efficient body structures, and pressure influencing growth patterns. Whatever the cause, many amphipods living in trench ecosystems possess bodies that stretch beyond the sizes expected for such simple creatures. Other benthic organisms include holothurians, deep-sea sea cucumbers. These creatures crawl slowly across the seafloor, consuming organic matter that drifts down from above. They play a significant role in recycling nutrients in trench ecosystems. Their bodies resemble elongated sacs with no rigid parts, making them ideal for high-pressure zones. Some species expand their bodies to move, others use feathery appendages to capture tiny particles. Their slow, deliberate movements reflect the energy constraints of the trench. In a world without sunlight, food must be conserved. Polychaete worms form another key part of the trench community. These worms burrow into sediment, feeding on detritus and microorganisms. The trench floor contains thin layers of organic material that gradually accumulate from the water above. While this material is not plentiful, it provides enough sustenance for organisms adapted to low-energy lifestyles. Polychaetes process this material, supporting a chain of life around them. Despite their simple appearance, they are vital to the ecosystem's function. Among the more unusual residents of the trench are small gelatinous organisms, animals with bodies composed mostly of water. Their shapes vary, but many resemble elongated blobs or drifting sacs. They often have minimal internal structures. Their bodies function with reduced metabolic demands, allowing them to live long periods without food. Because gelatinous animals lack dense tissue, pressure affects them very little. Their internal and external pressures equalize easily. These gelatinous creatures drift passively rather than swim actively. Energy conservation dominates their behavior. Any attempt to move quickly or aggressively would burn resources they cannot replace easily. Even their defensive strategies reflect this limitation. Rather than fleeing predators, they rely on transparency, slow movement, and low visibility to avoid detection. Another group influencing trench ecology are microorganisms. Bacteria and archaea thrive in the sediment, breaking down organic matter and producing chemical gradients. These microorganisms support larger species indirectly. Some bacteria form mats on the seafloor, providing feeding grounds for small grazers. Others survive within the guts of trench creatures, enabling digestion of material that would otherwise be unusable. Microbial communities adapt to pressure through modifications to their cell membranes, enzymes, and protein structures. These adaptations allow them to survive in environments that would prevent biochemical reactions in surface organisms. Microbial processes also influence the chemistry of the trench. They participate in nitrogen cycling, carbon processing, and methane regulation. Some microbes consume methane or produce it, shaping the geochemical system deep within the trench. Although their role is often invisible, they form the foundation for much of the food web. The scarcity of food defines nearly every biological strategy in the trench. Sunlight does not reach these depths, so photosynthesis is impossible. Instead, organisms rely entirely on the remnants of surface productivity. Dead plankton, fish waste, and fragments of organic material drift downward in a slow rain called marine snow. Larger food items like dead whales or fish occasionally reach the trench and create temporary hotspots of activity. Amphipods swarm these rare resources. Fish gather around them, microbes break them down. But these events are infrequent. Most of the time, trench life survives on minimal nourishment. This scarcity drives behaviours that appear strange from a surface perspective. Many trench species eat infrequently and digest slowly. Their metabolisms operate at a pace that would be impossible in warmer, more energetic environments. Predator-prey relationships exist but are less common than in other parts of the ocean. Predators must conserve energy. Fast chases are rare. Many creatures rely on ambush tactics or slow drifting to intercept prey. Some fish possess minimal musculature, using slow, deliberate movements to capture small animals. Predation still shapes ecosystems, but in quieter, more controlled ways. One of the most fascinating aspects of trench biology is the molecular adaptation of proteins. Pressure distorts protein structures, which affects nearly every biological function. To counter this, trench organisms use specialized molecules, like trimethylamine N-oxide (TMAO), to stabilize proteins. In shallower fish, TMAO levels increase with depth. At trench depths, levels become extremely high. This adaptation allows enzymes to operate at low temperatures and high pressures without denaturing. But it also affects taste and physiology. At extreme concentrations, TMAO contributes to the strong smell associated with deep-sea fish. This is why surface species cannot easily adapt to depth. Their proteins would collapse without these stabilizing molecules. Cell membranes also change composition. Lipid structures that maintain flexibility at surface pressure become rigid at depth. To avoid this, trench organisms incorporate different lipid molecules that remain fluid under compression. These modifications allow membranes to function properly, facilitating transport of nutrients and waste. Even sensory systems adapt. Vision is often reduced or absent. Instead of eyes, many organisms rely on touch or chemical detection. Fish may have small, simple eyes that detect dim bioluminescence or movement rather than detail. Some animals detect vibrations through their lateral lines. In the absence of light, these sensors become more valuable. Bioluminescence appears less frequently at full trench depth than in mid-water zones, but it still exists. Some organisms use faint flashes to communicate or distract predators. Others emit a glow as a byproduct of metabolic reactions. In the darkness of the trench, even a brief flicker can carry meaning. Yet because energy is scarce, bioluminescence tends to be dim and used sparingly. Most trench creatures have low reproductive rates. Producing offspring requires energy, and scarcity limits the number of eggs or larvae that can be sustained. Many deep-sea species lay fewer eggs than their shallow water relatives. Some release buoyant larvae that drift into mid-depth waters where food is more plentiful. Others produce larvae that remain near the sea floor. The reproductive strategies vary, but all reflect the constraints imposed by limited resources. Life in the trench also evolves slowly. Environmental conditions remain stable over long timescales, and extreme pressures limit the rate at which mutations produce viable new traits. Evolution here is guided not by rapid change but by stability in extreme conditions. Species that succeed do so because their ancestors gradually accumulated adaptations that made survival possible. Studying these creatures is difficult because the moment they are brought to the surface, they encounter a world their bodies cannot withstand. Pressure changes rapidly during ascent. Gases expand, proteins denature, membranes burst, muscles collapse. Many deep-sea animals disintegrate or lose structural integrity before reaching the surface. Some turn to jelly-like masses, others burst from internal pressure differences. This is why researchers must use specialized pressurized sampling containers to retrieve creatures without exposing them to surface conditions. Even then, maintaining stable temperature and pressure during ascent is challenging. These containers often require complex engineering to preserve specimens long enough for study. Because of these limitations, much of what we know about trench organisms comes from high-pressure laboratory experiments, comparisons with species in other trenches, and observations made during brief submersible missions. What we still don't know could easily fill volumes. We have only glimpsed a fraction of trench biodiversity. New species likely exist in sediment layers, along slopes, or in microhabitats created by chemical gradients. Some may rely on unusual metabolic pathways, others may form relationships with bacteria or archaea that have not yet been studied. Every dive brings the possibility of discovering something unexpected. Deep-sea environments like the Kermadec Trench represent one of the final biological frontiers on Earth. They reveal the extreme limits of life and challenge assumptions about what organisms need to survive. These adaptations also guide research into astrobiology. Studying trench life helps scientists consider how organisms might survive on icy moons or planets without sunlight. If life can exist under 10,000 meters of water on Earth, it may also exist beneath the ice of Europa or Enceladus. The trench becomes not only a biological environment but a conceptual bridge to other worlds. Yet despite the fascination surrounding trench life, we remain limited by the technology we can send into the depths. The creatures living in the Kermadec Trench exist in an environment that denies access to most machines. Pressure-resistant vehicles fail, cameras last only briefly, sensors drift, even sample containers struggle to reach the surface intact. As a result, our understanding of trench life grows slowly, piece by piece. What we do know suggests a biological system that thrives despite unyielding constraints. These creatures are not fragile. They are not temporary. They are not barely surviving. They are perfectly adapted. Their existence proves that life finds ways to persist, even when conditions appear inhospitable from our perspective. As we move forward, the focus shifts from the life within the trench to the challenges we face when trying to observe it. Even with pressure-resistant materials and carefully designed machines, our sensors and signals struggle to function at extreme depth. The environment swallows communications, distorts acoustic signals, and limits the reach of any instrument we send. Understanding these limitations is essential to understanding why the Kermadec Trench remains largely unexplored and why so much of its life stays hidden from view. Exploring the Kermadec Trench depends entirely on our ability to sense what we cannot see, hear, or touch directly. Every piece of information we gather, every image, measurement, map, or sample, passes through sensors that must survive an environment designed to break them. In the upper ocean, sensors behave predictably. Cameras capture sharp images, sonar beams travel efficiently, chemical analyzers process water samples without interference, signals move cleanly from one device to another. But as depth increases and the trench begins to assert its full force, these tools lose clarity, reliability, and endurance. Exploration becomes less a matter of observation and more a matter of inference. Machines continue to function on paper, but in practice everything becomes uncertain. The environment doesn't simply damage equipment, it reduces our ability to detect the damage. It takes our tools and makes them blind in ways that are subtle, delayed, or impossible to correct. The first limitation appears when sensors enter the thickening layers of water above the trench. Pressure increases steadily, but so does the density of the water. Sound moves faster in dense water, but it also bends. Temperature gradients create layers, each with its own density and sound propagation characteristics. These layers act like lenses, bending acoustic signals along curved paths. A sonar ping may drift upward, downward, or sideways, distorting the resulting map. A communication signal meant for a vehicle may scatter, making it arrive faint or delayed. Even slight changes in water composition alter how sound travels. Because so many deep-sea sensors depend on acoustics, mapping, navigation, communication, ranging, these distortions affect nearly every aspect of the mission. Sonar challenges become more severe as depth increases. At moderate depths, multi-beam sonar can generate high-resolution maps of the seafloor. But at trench depth, multi-beam systems lose much of their effectiveness. The return signals weaken, the beams widen, the angles distort. Even when sonar returns data, interpreting the information becomes difficult. A sharp ridge might appear rounded, a depression might seem flat, a slope might look steeper or gentler than it is. In a place where terrain shifts and machines rely heavily on sonar to navigate safely, these distortions create practical problems. Vehicles may drift too close to rocks or descend too quickly into depressions. A slight misinterpretation of sonar data can tilt an entire mission toward failure. Optical sensors face limitations long before the trench comes into view. Light does not travel far underwater. Even powerful, specially designed lights illuminate only a small area. Cameras depend on that illumination. But water absorbs light wavelengths unevenly, altering colours. Blue dominates. Reds, oranges and yellows disappear completely. This means cameras cannot accurately represent the colour or texture of most objects. Even when cameras capture images, the results are limited. Short range, blue-toned, and frequently obscured by particles suspended in the water. Suspended particles, known as marine snow or sediment, create backscatter that reflects light into the camera lens. The deeper a vehicle travels, the more pronounced this backscatter becomes. A well-lit scene on the seafloor often resembles a blizzard of drifting particles, even when the environment is calm. Engineers try to position lights away from cameras to reduce this effect, but doing so increases the complexity of the design. Mounting lights farther out requires more structural support, which increases weight and drag. Design changes ripple outward from small adjustments, forcing engineers to compromise between image clarity and structural feasibility. Many deep-sea missions depend on wide-angle cameras to capture the general environment, but wide-angle lenses warp when exposed to extreme pressure. Even small distortions in the lens shape change the resulting image. Focus becomes unreliable. Depth of field shrinks. Cameras may fog internally as cold temperatures affect internal air pockets or seals. A clear image captured at the surface often becomes hazy or vignetted at depth. Over time, pressure cycles weaken the lens material, leading to small fractures or clouding. Once that happens, the camera cannot be repaired easily during a mission. It becomes unreliable or fails completely. Chemical sensors, essential for understanding the trench's water chemistry, face their own set of challenges. These sensors measure dissolved oxygen, nutrients, pH levels, and trace elements. But chemical reactions slow dramatically near freezing. Electrochemical sensors produce weaker signals. Optical chemical sensors lose calibration. Many rely on one-time use reagents that behave unpredictably in extreme cold. When a sensor drifts out of calibration at depth, it may report inaccurate data for the remainder of the mission. Without consistent calibration at depth, which is difficult to achieve, researchers must correct the data after the fact using models built on assumptions. Pressure also affects chemical sensors. Many of these devices rely on pressure-equilibrated internal fluids. As the external pressure increases, those fluids compress unevenly. If the fluid compresses slightly more than expected, the sensor reads too low. If it compresses slightly less, it reads too high. Engineers can account for these changes in laboratories, but real ocean conditions differ from test conditions. Slight variations in salinity, dissolved gases, and temperature change fluid behaviour. These variations might be small near the surface, but become significant over the vast column of water above the trench. Magnetic sensors and compasses drift as well. The Earth's magnetic field behaves differently underwater, especially near tectonic boundaries. Metallic minerals in the seafloor distort magnetic lines. Compasses become unreliable. Some deep-sea vehicles use internal gyroscopes to maintain orientation, but gyroscopes accumulate error over time. Even small errors compound over hours-long missions. A vehicle that begins the mission oriented correctly may drift off course by several degrees, enough to miss targets or collide with terrain. Acoustic communication, one of the most critical components of trench exploration, is even more fragile than sonar. Signals travel upward through dense and stratified water layers. Along the way, they bend, weaken, and scatter. A command sent from the surface may take several seconds to reach the vehicle. In some cases, it never reaches the vehicle at all. Engineers must design communication systems capable of sending simple instructions repeatedly, hoping at least one transmission arrives intact. This creates limitations on what commands can be sent and how quickly they can be executed. Real-time control becomes impossible. Operators must rely on pre-programmed sequences and infrequent feedback. Because communication is limited, deep-sea vehicles often operate semi-autonomously. They follow programmed routes, carry out tasks, and then ascend after a set period. But autonomy relies on sensors to guide movement. If sensors drift, misread, or fail, the vehicle cannot correct itself. A navigation error early in the dive may grow into a large positional error by the time the vehicle reaches the trench floor. Without external reference points, the ocean is too dark and uniform for visual cues. The vehicle cannot recalibrate its position. This is why some vehicles vanish, not in dramatic accidents, but simply by drifting slightly off course until communication becomes impossible. Pressure affects the wiring inside sensors as well. Electrical conductors behave differently under compression. Internal connectors loosen. Solder joints crack. Insulation stiffens or shrinks. Sensors that rely on precise voltage or current measurements become unstable. A slight drop in temperature combined with pressure might distort sensor readings or cause intermittent failures. Engineers often discover these issues only upon recovery, when a careful inspection reveals microfractures or water ingress that explain the data anomalies. One of the most challenging aspects of deep-sea exploration is the inability to monitor most sensors directly while they operate. If a sensor drifts or fails at depth, the machine rarely communicates the failure clearly. Instead, it continues sending data that appear plausible but incorrect. These false readings can remain unnoticed until the vehicle returns, and researchers compare the data against expected patterns. In this way, the environment doesn't just damage sensors, it hides the damage behind a veil of functional but inaccurate readings. Sampling instruments face different limitations. Water collection bottles struggle to seal properly at depth. Pressure may force water through seals or prevent bottles from closing completely. If the bottle seals too early or too late, the sample may represent a mix of water layers rather than the intended depth. Sediment samplers may jam when internal parts contract due to cold. Some sediment cores collapse during ascent because gases expand, or because pressure differences cause the sediment to shift. Even when a sample reaches the surface intact, its chemical properties may have changed during the long ascent. Biological sampling devices struggle with similar problems. Nets and traps designed for shallow waters fail under pressure, losing shape or collapsing. Containers that hold fragile deep-sea organisms must remain pressurized throughout ascent. These containers require complex valve systems and strong housings. If the pressure difference is not managed precisely, the specimen inside may die or disintegrate. Many deep-sea creatures cannot survive even minor drops in pressure. This means the most delicate organisms remain largely undocumented, because capturing them alive without altering their physiology remains extremely difficult. One reason deep-sea exploration remains so limited is that most sensors are designed for mid-depths, not full trenches. Building full-depth sensors increases cost significantly. Every component must be redesigned, tested under pressure, tested under cold, and tested in combination. Even then, real-world performance may differ. As a result, researchers must prioritize which sensors to send down. They choose a few key measurements and accept that much of the environment will remain undocumented. Missions return with only partial datasets, forcing scientists to extrapolate the rest. Another factor is data storage. Vehicles must store massive amounts of data locally because communication bandwidth is extremely limited at depth. Storage devices must survive pressure and cold. Many storage systems rely on solid-state memory, which performs poorly at near freezing temperatures. Some systems include heaters or insulated housings, but these consume power and increase size. If a storage device fails during a mission, all collected data may be lost. Power limits further restrict what sensors can do. Cameras require constant illumination. Sonar consumes significant energy. chemical sensors draw power continuously to maintain temperature or control internal reactions. If the battery fails or drains too quickly, sensors shut down. Engineers must choose between running all sensors briefly or running a few sensors for longer periods. Each choice sacrifices some data. In some missions, engineers include redundancy, multiple sensors measuring the same variable. But redundancy increases weight, complexity, and cost. Many deep-sea missions operate on limited budgets. Even large, well-funded research programs cannot afford excessive redundancy. When a crucial sensor fails, the mission's scientific value may decline sharply. The limitations don't end when the vehicle returns to the surface. Data collected by sensors must be processed, corrected, and interpreted. Researchers must account for distortions caused by pressure, cold, darkness, and sensor drift. They must compare the data to models built from previous missions, aware that those models are incomplete. This creates a feedback loop where each mission clarifies some details but introduces new uncertainties. The trench environment shapes the data so strongly that scientists must interpret every measurement cautiously. A drop in temperature might reflect sensor drift rather than environmental change. A chemical spike might result from a container leak. A sonar anomaly might reflect a steep rock or a drifting cloud of sediment. Nothing can be accepted at face value. Every conclusion requires cross-checking with other data, and even then, certainty remains elusive. All of this means that exploring the Kermadec Trench often feels like trying to study a world through a thin, frost-covered window. The environment exists, rich and complex, but the tools we use to observe it distort what they see. Signals weaken, data drifts, and clarity fades. In this way, exploration becomes invisible, not because nothing is there, but because the environment erases our attempts to perceive it. The trench hides its true form behind layers of pressure, cold, darkness, and shifting terrain, making every mission a test of what sensors can withstand and how much information they can capture before failing. As we move forward, the focus turns to what these limitations mean for the future of exploration. Despite the challenges, scientists remain determined to push deeper, driven by the possibility of discoveries waiting far below the surface. But as the trench resists our attempts to understand it, the boundary between what we can observe and what remains hidden grows clear. In the next step of this journey, the attention shifts toward those future possibilities, how new technologies, evolving designs, and persistent curiosity could one day open the trench to deeper understanding and allow us to uncover what lies beyond the limits of today's instruments. Reaching the Kermadec Trench, truly reaching it, not just touching it for a fleeting hour or two, remains one of Earth's most difficult scientific dreams. Every attempt we make falls short not because our goals are unrealistic, but because the environment pushes back with a kind of quiet finality. And yet, even knowing the limits, the difficulties and the failures, the hope to uncover what lies at the bottom continues to guide researchers. It moves with them through long nights in ship laboratories, through engineering meetings where failures are dissected and redesigned, through the endless cycles of testing that eventually produce a machine capable of one more dive. These dreams don't shrink because the trench is difficult. They grow because difficulty is part of what makes discovery meaningful. Far below the waves, there are questions waiting. Questions about life, geology, chemistry, evolution, and even the origins of the planet. Scientists hope that by studying the trench more closely, they can fill gaps in our understanding that stretch across disciplines and time. The Kermadec Trench is not just another deep place. It is a location where Earth's processes converge in extreme forms, revealing patterns that are hidden in shallower waters. Exploring it is like looking at a magnified cross-section of the planet's most fundamental systems. What researchers hope to find is not a single treasure or landmark, but a set of insights that have been out of reach for centuries. One of the most compelling hopes is the discovery of completely unknown species, Life in the trench evolves under conditions that have no equivalent on land or in most of the ocean. Because of the extreme pressure, cold, and isolation, creatures here follow evolutionary paths unlike those in any other ecosystem. Every trench surveyed so far has produced species no one has seen before. Snailfish with translucent skin, amphipods with strange adaptations, microbes capable of chemical feats not found elsewhere. The Kermadec Trench, studied even less than others, almost certainly holds species that challenge our expectations. Some may be microscopic, others may be larger. All would reshape our understanding of biology's reach. The idea of discovering new species is not driven by curiosity alone. Each organism has a set of biochemical tools that allow it to survive conditions most life cannot. Those tools, the proteins, enzymes, membranes and molecules they use, carry information about how to engineer resilience in systems that must survive extreme environments. Studying these adaptations could help scientists design materials and biological systems that function under pressure, operate without oxygen, or remain stable at low temperatures. The trench may hold organisms with molecular strategies that inspire innovations in biotechnology, medicine, or materials science. We cannot be sure until we look more closely, but the potential exists. Researchers also hope to find new microbial communities in the sediment. These microscopic organisms may reveal how life processes chemical compounds in ways that do not rely on sunlight or abundant nutrients. Some microbes in other trenches use unusual pathways to extract energy from their environment. They oxidize chemicals found in the rocks, or use gradients created by shifting sediment layers. These processes mirror what might occur on other planets or moons. By studying the trench, scientists gain insight into what conditions might support life elsewhere. If microbes can survive at the bottom of the Kermadec Trench, they might exist beneath the ice of distant worlds where liquid water touches a rock under high pressure and complete darkness. Another dream involves the geological story hidden along the trench's steep walls. The Kermadec region lies along a major subduction zone, where the Pacific plate sinks beneath another fragment of Earth's crust. This process drives earthquakes, volcanic activity, and the formation of deep-sea trenches. But the details, how plates deform, how sediments move, how elements cycle between crust and ocean, remain mysterious. The trench floor may hold layers of sediment that preserve thousands of years of geological history. Each layer reveals something about past earthquakes, ocean chemistry, climate, and planet-wide change. Collecting samples from these layers could refine our models of Earth's long-term behaviour. Scientists are also interested in the chemical structure of the trench's waters and sediments. At great depths, water chemistry shifts in ways that are not fully understood. Dissolved elements behave differently. Minerals change structure. Organic molecules degrade slowly, creating unique chemical signatures. Studying these patterns can help researchers track global nutrient cycles and understand how carbon moves through the planet. Since trenches act as deep basins that collect material from across the ocean, they become time capsules of chemical history. There is equal interest in what might lie beneath the visible seafloor. Subduction zones draw water down into the mantle, where it interacts with rocks, alters their structure, and affects volcanic activity. By studying the trench more closely, scientists hope to understand how water moves through the Earth and how it influences magma formation and plate tectonics. Deep-sourced fluids emerging into the trench may carry clues about geological processes occurring far below the crust. These fluids could reveal information about the deep carbon cycle, a cycle that affects everything from global temperatures to volcanic emissions. Some researchers hope to identify new hydrothermal activity in or near the trench. While most hydrothermal vents lie in mid-ocean ridges rather than trenches, subduction zones can host unusual forms of venting. If such vents exist near the Kermadec Trench, they could support unique ecosystems unlike those found elsewhere. Discovering such a system would expand our understanding of deep-sea ecology and provide new examples of life thriving without sunlight. Vents also produce minerals and chemical compounds that influence ocean chemistry. Understanding them could help scientists model how the deep ocean interacts with the rest of the planet. There is also the hope of uncovering how trench ecosystems connect to each other. The world's deepest habitats are isolated, yet similar species exist in multiple trenches. Scientists want to understand how these species move between them. Do larvae drift for thousands of kilometers? Do mid-depth currents carry organisms from one trench to another? Or do separate populations evolve similar forms because the environments are so alike? Each trench might hold pieces of a larger evolutionary puzzle, and the Kermadec is one such piece waiting to be studied. One of the more ambitious dreams involves long-term observation. Scientists hope to one day build instruments capable of resting on the trench floor for months or even years. These instruments would record changes in sediment, water chemistry, seismic activity, and biological behaviour. With long-term data, researchers could understand patterns that currently appear chaotic. They could track how earthquakes alter the seafloor, how sediment moves after storms or landslides, and how populations of deep-sea organisms shift over time. But building an instrument capable of surviving that long remains far beyond current technology. Still, the hope exists, guiding the long-term goals of ocean research programs around the world. Another dream involves visual clarity. Cameras that can withstand pressure and cold long enough to observe natural behaviour of trench organisms would reveal moments we have never witnessed. At present, most images of trench life come from brief glimpses, organisms startled by lights, passing through illuminated zones, or reacting to sudden disturbances caused by machines. Scientists hope for the chance to observe these creatures without interference, to see how they feed, interact, and navigate their environment in unaltered conditions. Achieving this would require cameras that operate silently, without bright lights, and without producing heat or noise that changes the environment. It is a difficult problem, but not an impossible one. There is also a dream that feels more philosophical than concrete. The desire to understand the trench for what it is, not just as a scientific subject, but as a part of Earth that remains outside our control. In a world where satellites map the surface in detail and technology touches almost everything, the trench stands as one of the last places where human presence is minimal. Many researchers feel a sense of humility when they consider it. They hope that one day, exploration will allow us to appreciate the trench without diminishing its isolation. They want to understand it, not conquer it. Some dreams extend beyond biology and geology into engineering and long-distance exploration. The lessons learned from building deep-sea technology could influence the design of spacecraft intended for icy moons. The pressure-resistant housings, autonomous systems, and energy-efficient sensors developed for trench exploration may one day be used to explore oceans beneath alien ice. The trench becomes a proving ground not just for understanding Earth, but for preparing to explore other worlds. There is also the hope of building international collaboration. The trench lies near New Zealand and is surrounded by waters managed through treaties and cooperative agreements. Agencies and universities across the world share an interest in studying the region. Future missions may involve multinational teams combining expertise, resources, and technology. Large, coordinated efforts could make it possible to attempt bold projects that no single organization could accomplish alone. Beyond the scientific and technological ambitions, there are hopes rooted in the simple idea of witnessing something truly new. The possibility of discovering organisms that challenge everything we know about biology, the potential to observe geological formations shaped by forces too slow to see directly, the experience of seeing the seafloor undisturbed, untouched by machines in its raw natural state. These dreams motivate researchers even when machines fail, sensors break, and missions return with limited data. The Kermadec Trench inspires dreams because it resists exploration. Its depth, pressure, cold, terrain, and remoteness make it one of the Earth's final frontiers. And frontiers always carry the promise of discovery. a promise that persists even when the path remains blocked. For now, researchers continue pushing, diving, redesigning and returning, waiting for the moment when technology finally meets the environment's demands. But even with all the hopes tied to future discovery, the trench remains a reminder that some places stay beyond reach, not because we lack ambition, but because the planet itself imposes limits. That tension between curiosity and resistance defines the next part of the story. At some point, we must accept what cannot be reached today and consider whether the trench will always remain partially hidden, a place that refuses to surrender its full truth. Returning from the Kermadec Trench does not feel like a triumphant ascent. It feels more like withdrawing from a room that never invited us in. Everything about the journey back toward the surface reminds researchers of how little they touched, how much remained out of reach, and how the environment below left almost no trace of itself, except in the data that may or may not have survived the pressure. The return is not a victory lap. It is a slow, methodical retreat through layers of water that grow warmer, brighter, and more familiar with every metre, while the place left behind remains as distant as another world. For a machine at full trench depth, the process of returning begins long before it rises. Its internal systems must endure pressure, cold, and darkness while still carrying enough power to release ballast or activate ascent mechanisms. In some designs, small metal weights drop away, making the machine buoyant enough to drift upward. In others, compressed gas forces water out of chambers to create lift. Some vehicles release markers or acoustic signals to announce the descent has begun, but none of these systems guarantee success. A stuck ballast system, a jammed valve, or a battery drained too quickly by cold can leave a machine motionless on the seafloor. When this happens, there is little anyone can do. Recovery at those depths is virtually impossible. The trench keeps what it holds. For machines that do rise, the ascent can take hours. During that time, pressure decreases slowly. This shift affects every material and component. Housings expand as external force diminishes. Seals loosen. Fluids inside instruments move differently as pressure drops. Electronics begin warming and shifting out of their trench-adjusted behaviour. Parts that were compressed for hours begin stretching back toward their normal shapes. The entire vehicle undergoes a slow transformation as it travels through changing conditions. Engineers study ascent profiles carefully to anticipate these effects, but every machine reacts slightly differently. No two ascents produce identical behaviour. As the vehicle passes out of the deepest zone and into mid-ocean depths, new challenges appear. Temperature changes become more pronounced as the machine rises through layers of water with differing thermal signatures. Some layers warm quickly, others remain cool. These shifts create thermal stresses that move through the structure, expanding some materials faster than others. A camera housing might warm at a different rate than its mounting bracket. A steel frame might heat more slowly than a titanium component attached to it. These differential expansions produce tiny movements and stresses that rarely appear in shallow systems. Most of the time they remain manageable, but occasionally they cause cracks, distortions, or electrical failures during ascent. The water column above the trench contains pockets of variable salinity and density. As the vehicle rises, these pockets alter buoyancy, sometimes making the ascent slower or faster than predicted. A faster ascent might strain internal components. A slower ascent uses more power. Engineers calculate ascent speed carefully to avoid rapid decompression, because some components, especially pressure housings filled with oil or gas, must adjust gradually. A rapid decrease in pressure can cause these housings to deform or rupture. This is why ascent profiles follow strict guidelines, balancing speed with safety. Communication becomes more reliable as the vehicle rises. Acoustic signals travel more easily at moderate depths, and surface receivers can pick up location pings more clearly. For researchers waiting on the ship, these first signals are a relief. They mean the machine is alive, intact, and on its way back. But even with clear signals, the vehicle remains vulnerable. It may pass into layers of strong currents that push it off course. A drifting machine can surface kilometres from the expected location, making recovery difficult. Ships must reposition repeatedly, adjusting course to follow the vehicle's anticipated trajectory. As the vehicle nears the upper ocean, light returns in faint shades. Cameras inside transparent housings may pick up the first hints of illumination, but light brings its own problems. Sudden warming can fog lenses. Condensation may form on internal surfaces. If small leaks occurred at depth, water may evaporate or behave unpredictably as pressure drops. Even faint sunlight begins altering sensor behaviour, creating signals that must be filtered out later. Engineers design optical and electronic systems to account for these transitions, but failures still occur during this period. Biological materials collected by the vehicle undergo their own transformations. Sediment samples that remain stable at depth may begin releasing trapped gases during ascent. Pressure changes can rearrange layered sediment inside sampling cores, blurring distinctions between strata. Biological specimens may begin swelling, leaking, or degrading. Enzymes activate or deactivate. Cell membranes rupture. Microbial communities shift. Many samples lose their original characteristics long before the vehicle reaches the surface. Specialized pressure-retaining containers prevent some of these problems, but they introduce additional complexities and risks. A container designed to hold trench pressure must remain sealed during ascent, and then be opened safely at the surface without harming the specimen or the researchers. When the vehicle finally breaks the surface, the surrounding world feels ordinary compared to what lies below. Sunlight reflects off the waves. Wind rushes across the deck. The water is warm, the air is breathable, and the ship remains steady in ways the trench never allowed. The contrast feels unreal. The ocean surface seems calm, almost gentle, until one remembers the immense weight of the water directly beneath the hull. Most of that water does not appear in the footage or data. Cameras at depth capture small circles of illuminated sediment. Sensors record narrow snapshots of chemistry or sound. No instrument captures the full scope of what the trench is. The surface offers a reminder of how limited our glimpses truly are. Recovering the vehicle involves cranes, ropes, careful coordination, and a crew that has practiced the procedure countless times. Any mistake risks damaging the machine or losing it overboard. Salt spray coats everything. Metal becomes slippery. Waves shift unpredictably. The crew must watch every motion, guiding the vehicle gently onto the deck. Once secured, engineers rush to disconnect power, secure pressure housings, and stabilize temperature-sensitive components. They remove data storage devices, transfer samples into controlled environments, and inspect the machine for damage. These first moments reveal whether the mission succeeded. Sometimes the data is intact. Sometimes sensors failed early in the dive. Sometimes only fragments of the mission remain usable. The moment the vehicle is back on board, the trench becomes distant again. The machine, now resting on a steel deck under bright sky, carries only pieces of that hidden world. Engineers examine cracked housings, bent mounts, loosened cables, or distorted components. They compare the machine's state to its condition before the dive. Each imperfection tells a story about the environment it encountered, where the pressure was strongest, where the cold seeped deepest, where currents pulled unexpectedly. These post-dive inspections become lessons for future missions. The trench reveals its presence through what it breaks. Scientists move samples into climate-controlled rooms. They begin analysing water chemistry, sediment composition, and biological material. Some samples need immediate attention. Chemical signatures may shift quickly. Microbial activity may resume or change. The longer samples remain in surface conditions, the more their original properties fade. Researchers work quickly, knowing that some information is already lost. Meanwhile, the crew on deck prepares the vessel for the next stage. The machine may need repairs before another dive. Replacement parts must be installed. Cracked components must be removed. Engineers mark areas of concern for later reinforcement. They examine data logs to identify when and where sensors began drifting. They attempt to match failures to specific depths or environmental conditions. Every detail becomes important. Each mission carries its own lessons, and those lessons shape the next attempt. For scientists, the ascent marks the beginning of interpretation. They sort through data to distinguish genuine environmental signals from sensor drift. They compare results against previous missions, seeking patterns. They note inconsistencies, uncertainties, and gaps. Much of deep-sea research involves accepting ambiguity. The trench does not reveal clear, unmistakable truths. It offers clues that require careful analysis, cross-referencing, and cautious interpretation. For many researchers, the return to the surface carries mixed emotions. There is relief that the mission ended safely, pride in what the machine accomplished, excitement about the data. But there's also a quiet sense of incompleteness. The trench remains mostly unknown. Even the best missions reveal only small slices of its complexity. There is always more to understand, more to improve, more to attempt. The surface represents a boundary, one we cross easily compared to the limits below, yet one that marks the point where the trench becomes memory rather than presence. Ascending into familiar air reminds us how alien the deep world truly is. The environment on deck feels stable and warm. Pressure drops to what humans consider normal. The contrast is so stark that it can make the entire dive feel unreal, as if the trench were not part of the same planet. Yet despite this distance, each return reinforces the desire to try again. The surface becomes the place where plans are made, tools are refined, and ideas begin forming for the next mission. The trench rarely allows direct contact, but it leaves a lasting pull. Researchers speak about it with a mix of respect and determination. They know it cannot be tamed or fully explored, but they continue seeking ways to reach deeper, stay longer, and understand more. Returning home after studying the trench, whether that home is a research vessel, a laboratory on shore, or a university office, brings reflection. The data must be analysed, the equipment repaired, and the next mission planned. The trench becomes something imagined rather than seen, reconstructed through incomplete images, partial readings, and careful interpretation. It becomes a place held in fragments and possibilities, rather than direct experience. But even with its distance, the trench remains compelling. Researchers understand that they may never fully touch it, not with current technology, not with any foreseeable advancements. The environment simply pushes too hard, resists too consistently, and hides too effectively. Yet this limitation does not diminish the value of the journey. It enhances it. The surface reminds us of our place. It shows us the boundary between the world we inhabit and the world that continues without us. It gives us a space to breathe, think, and recalibrate before facing the limits again. In that space, the trench becomes an idea as much as a location, a reminder that our planet still holds places where human presence is temporary and incomplete. And so, returning home from a place we cannot touch becomes part of the rhythm of exploration. We go down, we learn what we can, we return, and we prepare to try again. The trench remains below, unchanged by our attempts, waiting for the next moment when we gather the courage, the tools, and the determination to approach its depths once more, knowing full well that reaching it fully may never be possible, but understanding that the pursuit itself continues to shape our knowledge of the world.